The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with one half to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity.
Good morning, everybody around the world. Welcome to day 2 of the special online event honoring Roger Penrose. And we're a little late. We're going to get right into the program. So let me just make an announcement that the chat line is disabled. We had some technical problems yesterday. It was annoying people and some other issues. So the Q&A line will be open to submit questions. And without further ado, I'd like to introduce Roger Blandford, who spoke yesterday, and he will be chairing today's session. Roger, take it over, please.
Hi, thank you very much, Stuart. As we're running a bit behind, just to add my welcome to the session on quantum measurement and objective reduction, which will happen today for the next 3.5 hours. I'm not going to give extensive introductions to the speakers because we've already lost a little bit of time, as you heard from technical problems. So let me just say the first speaker will be Professor Yvette Fuentes-Guerridi from the University of Southampton, and she's going to speak about the exploring the unification of quantum theory and general relativity using a Bose-Einstein condensate. So share your screen, Yvette, and you have 45 minutes.
Well, thanks for that, and I want to start by wishing Roger happy birthday on behalf of my group and our common collaborators and friends, also my family. So it's been many years of having the honor of knowing and spending time with Roger, talking about physics and so on. So it's really like a great honor and a great pleasure to have the chance to give this talk. And very special thanks to Stuart for this very special invitation. So yes, like you heard, I'm going to be talking about how can we use Bose-Einstein condensates to make progress in our understanding of the interplay between quantum mechanics and general relativity. So there are many fundamental questions in physics which are still unanswered. So for example, does the equivalence principle hold for quantum physics? So Roger gave a very nice talk yesterday, and in the talk he explained how he thinks that there is a conflict, or he has strong arguments to show that there is a conflict between the equivalence principle in general relativity and the superposition principle in quantum mechanics. There's many other interesting questions, like, for example, what is the nature of dark matter? Or what's the physics that dominates the universe? Is dark energy driving the accelerated expansion of the universe? So Roger thinks that not, I think he thinks that not. Maybe he can say something later, but sometimes, you know, when I comment on me trying to come up with ideas on how to, let's say, constrain models, he's mentioned that, and I always think, well, then it's a good thing that we find ways on how to falsify theories in that case. But well, these are all very interesting open questions. But underpinning all of these questions, or most of the questions that are still unopen, is the fact that quantum mechanics and general relativity are incompatible. So now in the UK, but maybe also in many other places, it's become sort of a big topic on how can we use quantum technologies to address fundamental questions in physics. And we were having a very nice school organized for that. And someone in the audience pointed this out, saying that, well, the elephant in the room, is how he put it, is that we just don't understand scales in which these two theories interplay. And this really is underpinning many of the other interesting questions that are still unanswered. So in quantum theory, the Schrödinger equation obeys Lorentz transformation, so time is absolute. And space and time are very different notions. In the Schrödinger equation, for example, space, there's a second derivative in space and just the first derivative in time. So they're treated very differently. Positions are described with operators, and time is just a parameter. So again, space and time play a very different role in the theory. And then we get that quantum states can be in superpositions of different states. In particular, for example, we could find that a particle can be in a superposition of two different positions at the same time. Then contrary to this, in relativity, time is observer dependent, not absolute. And actually, one of the most radical things that we learned from Einstein is that space and time are not so different, but they belong together in something that we call space-time. And if space-time is curved, then we can find that time might flow at different rates in different points in space. So we don't really understand how the interplay of these effects takes place in nature. So here I have a picture of Roger thinking and asking, should we quantize gravity or should we gravitize quantum theory? So this means, because that's something that we discussed and I actually learned from him. So quantizing gravity would imply keeping the foundations of quantum mechanics, the principles of quantum mechanics, and modifying gravity to, you know, kind of to come together in a consistent way. And there's a lot of work done in this direction, but gravitizing quantum theory would mean the contrary, would mean we keep the principles of general relativity, and we then change quantum mechanics. And this is something that Roger thinks would be the best route to take, because in quantum mechanics, although it can explain and it can predict the results of experiments with huge accuracy, there is a big problem, which is the measurement problem, which we can't explain. Why, when we make a measurement, suddenly a superposition collapses into one or the other answer. So in that sense, he feels that anyway, quantum theory has to be modified. But I guess we both agree that perhaps in a full theory, both theories will have to be modified. And in my opinion, the most important question to answer at the moment is space-time can be in a superposition of different configurations. And this is because if we have a massive system, like for example, the Earth, but already at, let's say at systems that are having 10 to the 14 atoms, this might become already in experiments interesting. So if we have, but for now, let's think of the Earth. If we have the Earth, it curves space-time. And then if we can have the Earth in a superposition of two different positions, then it would imply that we could have the gravitational field in a superposition of two different configurations. And we don't know if that's possible. So it is possible with the electromagnetic field. If you have a charge has an electric field. And if you have the charge in a superposition of two different positions, we know that the electromagnetic field, and we tested this in experiments, the electromagnetic field can be in quantum states. But we don't know if this is the same case for the gravitational field. And the problem is that when we think about the scales in which quantum mechanics and general relativity interplay, we don't have any instruments or any experiments to guide our understanding and our theories. So I put this picture here because I like it. I like to think about how it was when we didn't have telescopes and people would just look into the sky and see stars and then try to make sense of cosmology and make cosmological theories. So it's very difficult when you don't have an instrument to make sensible theories. So then Galileo invented the telescope, and it developed and it has been really reaching incredible sensitivities and capabilities. And we've learned then that the universe is expanding and that there's galaxies out there and all of these things. And then we can start making more sensible theories of cosmology and astrophysics and so on. The same thing happens if you think about the very small. The Greeks came up with the idea of the atom, but it's not until you build a microscope and you actually start to look at the microscopic world that you can really start making more sensible atomic physics. So I really believe that we first need to develop the experiments and the instruments before we can start making real progress in the direction of understanding quantum mechanics and general the interplay of quantum mechanics and general relativity. And I mean, I think we can make a lot of progress with mathematics and with theory. And we have so far, I think, but we also have reached the point in which in order to continue to develop, we really do need these experiments and these instruments at this scale. So my research, more than trying to theoretically or mathematically come up with ideas of how to understand the interplay of these theories, I've been focusing more on how can we develop these new instruments that will allow to open a window to these scales where we can expect new physics. So, well, there's been a huge development in the last years in quantum technologies, and a lot of it has been focusing on commercial applications and on things like quantum computers, quantum cryptography, quantum communications. And it's really been a lot of progress in the last years. And I think one of the reasons why this has developed so fast is exactly because we have that interplay between theory and experiment. So we come up with ideas like entanglement, theories of entanglement, and then we can go to the laboratory and test them. And then you get this feedback that allows you to make progress very fast. But you can also use these technologies not only for computers or for quantum communication, but you could also be using these technologies in order to address and trying to understand fundamental questions in physics. So when we think about quantum mechanics, well, at least when I learned it many years ago, the idea was that this was a theory that applied to very small scales where electrons and atoms live. And that general relativity applied to the large scale. So let's say starting with the solar system into the Milky Way and beyond that. But it's very interesting that we have learned for quantum technologies in the last years is that this division has become very, very blurry. So let me show you what I mean by this. So in the last years, there's been huge progress on quantum technologies in space. So for example, there's been a satellite launched by a Chinese group, which is dedicated just to do quantum experiments. And they've been able to distribute entanglement across thousands of kilometers. So the idea that quantum mechanics belongs to small scales in space, now, well, our understanding of that has changed. You can entangle photons at those very, very large distances. And something which is very interesting is that at the scales where satellites operate, we know from GPS that relativity kicks in. So GPS, in order to have the precision that it has, it needs to make corrections using general relativity, because the proper time on Earth and on the satellite is different due to the curvature of space-time. So this is a line of research that I'm also interested in, and I have a series of papers in that direction explaining how the curvature of space-time and relativistic effects might affect quantum cryptography, quantum teleportation, and entanglement, and so on. I'm not going to talk about that, but that is one direction in which you can see that thanks to the developments in quantum technologies, we've learned that quantum mechanics doesn't necessarily only apply to small spatial scales. Another thing that we've learned, because also when I learned quantum mechanics, maybe it was too long ago, that it applied just to a few particles. However, it's been possible to put up to 10 to the 10 atoms in a state that we called a Bose-Einstein condensate, where the whole system behaves like a big quantum system. So you can put it in superpositions of different states. So I'm going to talk a little bit about that, because that is work that Roger and Richard Howell and I did together. So, well, the beautiful thing about Bose-Einstein condensates is that you can cool them down to 0.5 nanokelvin. So they're the coldest experiments that we can make on Earth. So you can trap the atoms. For example, typical atoms would be rubidium or sodium or cesium, and you trap them with lasers. And there is a number of different techniques to cool them down. So here you can see atoms in a quadratic potential, and in this case, they're in a thermal distribution, so they occupy different vibrational states. But when you apply your cooling techniques, you can make all the atoms go into the ground states. So the atoms are bosons, so then they can all occupy the same quantum state, and particularly in this case, the vacuum state. So when you do that, the atoms the wave functions overlap of all the atoms, and they don't behave individually anymore. They behave like a big quantum system. So you can also put the BEC in a double well potential. So here you can see a little drawing I made of the atoms in a double well potential. Some can be in the left, some can be in the right. But a actually quite difficult state to prepare would be called a Schrödinger cat state, or a null state, in which you have all the atoms in the left well, and then that state in superposition with all the atoms being on the right well. So this, like I said, is a state which is difficult to create in a Bose-Einstein condensate, but if we could create such a state, then we could test gravitational induced collapse. So Roger told you the basics of that yesterday. So the main idea is that there is an inconsistency between the equivalence principle and the superposition principle. So if you had a massive system in superposition, this would not be a stable state. So due to gravity, the quantum superposition would collapse into either left or right. And there is a time at which you could expect this to occur. So at the moment in quantum experiments, we can put, let's say, single atoms in superpositions of different places. And we don't observe this gravitation-induced collapse. But according to Roger's theory, this should be observed. It's just that the time scale that is associated to this would be very long. So practically, we just don't see it in the experiment. However, if instead of having atoms, you have more massive systems, like let's say a bead or so on, then you would see the collapse. Sorry, I heard something. Was there someone trying to say something? Okay, I'm gonna go faster because I think I'm going super slow. So in order to get the time scale, there's an important quantity which is called the gravitational self energy. I'm gonna talk a little bit about that this specific equation in the previous and in another slide. But if you take a uniform sphere of radius r, then and you think about creating a superposition of the sphere with itself separated by a distance b, then the gravitational self energy would be given by these equations here, where lambda is the quotient of the separation divided by 2 times the radius. So this is what was known before. This is a calculation made by Roger. And from this, you can estimate how big the mass has to be and the radius of the system in order for you to see collapse. So what we did is that and you're going to hear a lot about that today. There are several talks coming up on how can you test this using nanobeads or mirrors. There's some experiments using diamonds and so on. But we've thought about using BECs, and I'm going to tell you why we think this is an interesting thing to consider. But BECs, you have the atoms in a potential and you can change the shape, not just the spheres. And we looked at how would the collapse time change depending on the geometry of the BEC. And it's highly dependent on their geometry. And actually here you can see this A and B settings. And in these two cases, actually, the collapse times occur faster. So you want the collapse to occur faster than decoherence. I'm going to tell you a little bit about that in a moment. So in a way, by picking these geometries, you might have some advantages. This would also apply for nanobeads and other systems as well so far. And the other thing that is interesting about this is that when the system collapses, it depends on the geometry. So this gives you a signature because there's many things that make the quantum state collapse. And I'm going to talk about that in a moment, but it's basically noise. But noise has a very different signature. The noise does not depend on the geometry of the system. So because of this geometry, the dependence on the geometry of the system, you should be able to distinguish the theory that Roger proposed compared to just any other source of decoherence. So we found, you can see here in these plots, how for some ellipticities, not in all cases, certain geometries are more favorable. So for example, this is the sphere for ellipticities that are like almost close to 1. But if you go to lower ones, then you start getting that A and B, the configurations I showed you before, actually collapse at shorter times. Now, a BEC doesn't have, these are calculations for uniform densities, but BECs don't have uniform densities. So what we did is that we calculated the time at which you would expect gravitational induced collapse for different geometries and different density models for the BEC. And we found that actually the fact that the density is not uniform in a BEC is also giving you an advantage. This, for example, in this plot, you can see this is the uniform sphere, and this is a sphere that has the non-uniform density in the BEC, and you can see that the collapse time occurs before. So that also gives you an advantage. But there's many things that make the collapse of the wave function occur, which are not due to gravity. So one of them is three body recombinations. So three particles can collide and then you lose them from the potential because the potential doesn't trap the joint system. You also have two body losses, interactions with the thermal cloud, interactions with other atoms, as you can see here, and just decoherence coming from the trapping potential. So what we did in the paper with Richard and Roger is that we studied all these different types of decoherence to get an estimate of how big would the BEC have to be and what conditions would it have to satisfy in order for us to see gravitational induced collapse. So what we found is, well, there's a parameter that is unknown in the theory. So it depends a bit on this parameter, but you could think about more or less having 10 to the 9 atoms in 1 micrometer, and then that would give you decoherence in 2 seconds. So you would have to have, collapse into 2 seconds. You would have to have decoherence bigger than that. And well, this is still, let's say, not doable in current experiments, but it's thinkable if we are able to, let's say, develop new experiments targeted in these directions. It's not unthinkable. So that's one of the things that we're working on, is with experimentalists, as working out all the details so that we can do this experiment. And this is what we want to do next. We're also in a BC, you have something very special. So you're gonna hear about how can you test this with nanobeads and mirrors and systems like that, which are solids. But in a BC, the atoms are not bounded. So if you have a superposition in a potential, you can have some atoms tunneling from one potential to another. So we're trying to work with Chris Westbrook. How can you use this effect in order to detect gravitational induced collapse at lower masses? And that also gives you a variety of quantum states that are not available in solids. And that is something that we're also working with Roger in trying to come up with formulas of gravitational induced collapse for this variety of states that are accessible to BECs, but not to solids. Okay. So we talked about how quantum technologies are reaching scales where you can expect having relativistic effects by going to very large distances in space, using satellites, or by using very massive systems that you can in principle put in superpositions and expect gravitational effects. Another direction in which you could expect quantum technologies reaching scales in which you might see relativistic effects is because of the high precision of quantum systems. So there's a beautiful experiment done in NIST in which they had a quantum clock. This is the most precise ways of measuring time. And they then took the clock and made measurements at 33 centimeters, and they found time dilation. So when I told my colleagues that I wanted to use quantum systems like VEC to measure curvature of space-time, they told me I was crazy because at those scales, at small scales, space-time is basically flat. But what they were not taking into account is that the precision of quantum systems is so high that when you get, for example, here with the atomic clock, sorry, I went, it can measure time with an accuracy of 10 to the minus 18. So with these accuracies, you can start seeing time dilation. Actually now, before it was 33 centimeters, now you can see it at 1 centimeter. So if you see time dilation, you're basically seeing the effects of the curvature of space-time at those very small scales. And actually the way in which we measure gravity more precisely is using atom interferometry. So in this case, we take a bunch of atoms that do not interact. They're all like individual atoms, and we throw them into an interferometer. So these are some lasers that make each atom go in 2 different trajectories at the same time and then recombine. The trajectories are made such that they're different and they pick up information about the local gravitational field. So it's single particle in the sense that there's no interactions and each particle goes through different trajectories. It's local in the sense that the interaction takes place at a point. And the precision is limited by the time of flight. So the bigger the interferometer, the more precise it is. So you can see here how the accuracy in measuring the gravitational field depends inversely as the time of flight squared. And this is compatible with Newtonian physics in the same sense that when we describe this, we use the Schrödinger equation. So then we can use Newtonian physics in a compatible way to describe what's going on. And because the precision depends on really long interferometer arms, these sort of interferometers are going bigger and bigger. So this is a wonderful experiment by Philippe Boyer, who's one of my collaborators, in which he flew on a plane in free fall with an atom interferometer to get very long lengths. And he also has a wonderful experiment being built underground in which each arm is 300 meters, and he's going to make some atom interferometer underground. And we've been also applying for grants with a colleague of ours, Ernst Russell, who has a tower in Germany in which it's like 20 meters tall, I think, and they drop atoms in order to test the equivalence principle. So these interferometers are going bigger and bigger and bigger. There's also rockets, for example, made in Berlin and in other places as well, not with atoms, but with light. There's also plans to make light interferometers to measure gravitational waves in space. So this is LISA. So it's always about going bigger and bigger and bigger, but I want to go small. I want to measure gravitational fields in something very small, in a chip, in a phone. So with that paradigm, we can't do it because the equation is very simple and it just depends on the time of flight. So if you want to shrink it, you just lose sensitivity. There's actually some work in which they try to miniaturize these detectors, but the paradigm is the same. So here you have, again, the superposition in space of atoms. And what they do is that they interact with them with an electromagnetic field in order to slow them down. But the idea is basically the same. So what I've done with my group is that I proposed a different way in which to measure gravitational effects. So you could, by this, measure, for example, the local gravitational field or gravitational waves. Also, we have some work on dark matter and constraining dark energy models. And the main idea is that instead of having atoms in free fall, you trap them. So when you trap them, they interact and they create collective mode of excitations that we call phonos. So now the interferometers that we talked about before are interferometers in space. You're using atoms that are in a superposition of two different positions at the same time. Whereas here, the states are non-local. The atoms are quantum mechanically non-local. You can't tell where they are in the box. But what's sharp is the frequency of the modes, because in quantum mechanics, you have this funny thing that if you have something very localized in space, it's spread in momentum and vice versa. So that's what we're using here, that we're looking at states in which the atoms are undetermined in space, but very precise in momentum. And then we do interferometry in this frequency domain. So by doing that, we're able to miniaturize detectors. And not only that, this is compatible now with gravity, with general relativity, because in, the whole way we developed this was not using Schrödinger equation and non-relativistic quantum mechanics, but our theory is underpinned, or our proposal is underpinned by quantum field theory in curved space-time. So quantum field theory in curved space-time is a way of bringing together quantum mechanics and general relativity in a consistent way. So it considers space-time to be classical it's like in general relativity, it's curved, but it does not have quantum states. So in that sense, it's classical. And then you see how quantum fields behave on it. So in that sense, it's semi-classical. The one thing it doesn't address is the interesting question, which is how can a massive system curve space-time and put that into a superposition. So quantum field theory in curved space-time is a theory that doesn't allow you to ask questions in that direction, but it does allow you to think about some questions in the interplay of quantum mechanics and general relativity, as long as you constrain to low energies and you don't see what is the back reaction, how the quantum systems that you're studying curve the space-time. So in that way, it's like an intermediate theory, but it does allow you to address very interesting questions. So in the proposal that we have a BC and we have the frequency modes in that BC, and we prepare them in a superposition of states, in this case with the sharp frequency states. Then something happens to your system. So for example, a gravitational wave comes by, or you put a source of dark energy close to it. Or you want to measure the local gravitational field. So that's going to change your modes, and then you sort of apply a transformation that corresponds to closing your trajectory, but in the frequency domain. I don't want to go into those technical things, but we've studied what we can do with such a thing, and we found we have some proposals on how to measure continuous source gravitational waves, constrained dark energy models, measure curvature, for example. And we've shown that you can get very good accuracies by doing that. So when you have the superposition in space of atom interferometry, the precision depends on how big your interferometer is. But because now we're using interferometry in frequency, which basically means in time, you don't need to be big. You can be very small, but then the precision depends on how long your states live. So here there is an experiment, there's an example of an experiment making a BC very small and putting it in a chip. So that is one of the things that we're interested in terms of measuring local gravitational fields, that in the future, bring this idea together with the technology, you might be able to put a gravimeter on a phone like I would like to. I'm going to jump these things because of time. So these are more technical details on this idea. These are the sensitivity curves that we get for our prediction. So these are the frequencies and these are the sensitivities. They depend on many different things like the scattering length of the atoms in the BC, the number of atoms you can squeeze. But what I want to show you, these are models of continuous source gravitational waves with neutron stars. So in principle, the sensitivities that we get look quite promising. And we also plotted these together with the known detectors for gravitational waves like LIGO and LISA and so on, to show that we actually, where LIGO loses sensitivity, that's where this proposal in principle should start working. And these are frequencies at which there is no known sources for gravitational waves. So these would be exotic sources. For example, dark matter, ultralight dark matter models and so on. And well, Roger told you about his CCC model for cosmology, and part of CCC is that he would expect dark matter to decay. And this would send very specific signals. And one of the things that Roger got interested into these proposals is thinking that maybe there could be useful in order to detect some of these dark matter decay signals in CCC. So that's work in progress because we still don't know how quite a bit of work to do in that direction in order to say anything. I think I'm running out of time, so I'm just gonna stop here. This is just commenting on how dark matter, what are the scales in which we could in principle detect dark matter. This is about why it works being so small. So maybe if there's a question in that direction, I go back to that. But we also have very good results in future possibilities and experiments for constraining dark energy, and as well as commercial applications in detecting the local gravitational field. So I'm going to end here. I hope I was able to raise interest and curiosity on how you could use BECs in order to make progress in our understanding of scales in which we can expect quantum mechanics and general relativity to interplay. I think quantum technologies have made recently a lot of progress, and I think we're about to see many interesting proposals on how we can use this to make progress in fundamental physics.
Oh, thank you very much indeed, Yvette, for a lovely and fascinating discussion of these experimental initiatives and the theory that underlies them. I've got lots of questions, and I'm sure everybody else has, and I wish you'd have been able to have much more time to show your slides. But I think what we've decided to do is to withhold all the questions till the discussion at the end, so we can get all the sort of talks in front of us, and then let's have a very good discussion at noon. So thank you again very much for a lovely presentation, and let's move forward with Hendrik Ulbrecht, also from the University of Southampton, and he's going to probe new physics by levitated mechanical systems. So if you can remove your screen sharing, Yvette, and Hendrik can add his. Thank you very much.
So thanks a lot for having me. Also my heartiest congratulations to Roger for the birthday, which is coming up next week, if I'm informed correctly, and also, of course, for the Nobel Prize. I think for me personally, I'm most grateful for the encouragement which I get from looking at Roger's work and all these ideas, and also seeing how from ideas one can develop a theory, a model towards predictions of results of tests. So that's very encouraging, and there are many of those examples in Roger's work. So okay, so let me talk about levitated mechanical systems. So that's a platform which is also a hot candidate, if I may say so, to test the quantum superposition principle, to probe into the collapse of the wave function, or into objective reduction models and ideas, if you prefer that language. So levitated systems are basically, if you see my cursor on my mouse here, it's basically a fancy name for taking a big particle which consists of many, many atoms and suspended by a force field which can be magnetic, or it can be an optical field, a laser, or it can be an electrical field. So this is an example here of a magnetic levitation, and the particle you see here is 3 millimeters. So that is a really, really big and macroscopic object in that context. So it's much bigger than the atoms Yvette talked about. And these are some experiments which I will come back to during my talk. We also do experiments with much smaller particles where this diameter, this size is on the order of 100 nanometers. Yeah, so that is these experiments. So I have a little summary. So I have the intention to stay in time to make it like a nice presentation. I will try to show you nice pictures of the experiments we are doing, but also of work which I have been involved with in proposing experiments to probe into the collapse of the wave function, but also the interplay between quantum mechanics and gravity. Yeah? And there are specific ideas which are around those levitated experiments. So here's a list of things. So that's my plan. I hope I can at least make it through half of it. So I will talk about experiments with levitated optomechanics. I will show you a little bit how these experiments are done and what we can do already now. What are the tests which we can do? Then I will talk about testing of collapse of the wave function in the context of so-called CSL models, so continuous spontaneous localization models, which we can also already test with some of these experiments. And then I talk about some of these recent proposals where I have been involved with in probing into gravity and quantum mechanics. So now the idea here is very simple. So we say we have a system, these levitated particles, which on one hand are still small enough so that we can generate spatial superposition. So we can generate the superposition of the particle being in one location plus the particle being in the other location. So that's what I call a spatial superposition. So we have systems where we still can do that, or we hope to be able to do it in a very near future. And at the same time, these systems have already so much mass so that gravity may play a role, start to play a role, and acting on those superpositions. So that is the parameter regime where we think there's interesting things which we can do. If I have time, I will mention experiments with these levitated magnets, and then because it's such a nice platform, you can also probe in lots of other physics, including dark matter and dark energy. I'm not sure I make it, so I just start off. And I first start to talk about superpositions, testing the quantum superposition principle. So that was also mentioned by Yvette, and Roger talked about this yesterday. That's the cornerstone of quantum mechanics, and it basically tells us that if one wave function is a solution of the Schrödinger equation and another is also a solution, then we can superimpose the two, and the superposition of the two is also a solution of the same Schrödinger equation, and that holds for energies, for momenta, but also for spatial states, and that is in a way, oh, I'm sorry, that is very blurred, but I hope you can still see it. So that is basically what is behind the double slit experiment. I maybe move to the next slide because that is really of low quality. So here you see, if you want, the world record of the double slit experiment. So where people, in this case in Vienna, Markus Arndt's group, they have shown that these spatial superpositions, so one big particle, in their case, it's a big organic molecule. So you see it here on the left-hand side of the slide. It's a big organic molecule, which is especially synthesized for that experiment, that is put in a spatial superposition state. So that is happening in this interferometer here, which is a very complicated machine. So they have pushed this really to the technical limits. So the distance, just to give you an idea, as it's also indicated here, the distance between the first and the last greeting is 2 meters. So that is a massive apparatus, and they basically generate a beam of these big particles. 2,000 atoms are combined chemically into one of those molecules, and they fire them through the interferometer, and then they detect the interference pattern, and they still see up to a mass of 25,000 atomic mass units in interference pattern. And if they see this interference pattern, then that's a proof that the spatial superposition state is still possible for a particle of that mass. Yeah, so 25,000 atomic mass units, it's roughly 25,000 times the mass of an hydrogen atom. So that is where actually the limit of quantum mechanics in that context of spatial superposition states actually is at the moment. Yeah, so that is the biggest object which has been put in such a superposition. Okay, so now what I want to do is I want to push this limit. Yeah, and I'm trying to do this for the past 15 years already. The idea is to use these nanoparticles, these beads. So you see an electron microscope image here on the left-hand side. These are these particles which have roughly 100 nanometer in diameter. And I will tell you a little bit about the experiments which we can do, not only in my group, but there's a whole community now with maybe 10 to 20 groups around the globe, and they do what is now called levitated optomechanics. So what we do is we take a laser, we focus the laser beam, and in this tiny laser spot, we trap one of these nanoparticles. They are glass particles, so silicon dioxide, and they're mostly transparent to the light we are using, so there's no absorption, and that enables us to use the optical dipole force or gradient force to trap the particles. So it's very similar to what is called in biology and chemistry an optical tweezer. So that's a technique which has been developed by Arthur Eshkin in the 1980s and 70s before cold atoms actually came up. So there's also an interesting, historically, an interesting, you know, liaison or a relation between optical trapping of macroscopic objects like these nanoparticles, and then learning how to do it with atoms and starting to do cold atom physics. I have no time to go into this. It's very interesting. So Arthur Eshken, he basically showed us how to do optical tweezers. And what we are doing is we're doing this in vacuum chambers. Yeah? So we are not trapping in solution, which is the typical environment for an optical tweezer. We have a vacuum system, which is indicated here, which can be ultra high vacuum. So for experts, 10 to minus 9, 10 to minus 10 millibar, something like that. And we can trap a single particle in this laser beam. And then we can use the same laser to actually detect the motion of the particle. Yeah? So the laser is forming a harmonic trap, and the particle is oscillating in this harmonic trap, and we can use the same laser to detect the position and the motion of the particle. And that is, you have to believe me, one of the best harmonic oscillators which there is. And you can see this in this nice spectrum here. So that is the time trace. You see basically how the position is changing over time. And then if you do a Fourier transform, you can see a nice peak there, which is the mechanical resonance frequency of this oscillation. So, and that is the starting point. We started to get into this in around 2015 or so, and other people also did join this and did experiments. So what we can do by now is we can actually also use the same optical field to affect the motion of the particle. We can squeeze the motion of the particle. So these are plots which show, again, for experts, the phase space. So that is velocity or momentum versus position. And then you can generate interesting motional states of this very massive objects. You can cool the center of mass motion. So some people have now realized the ground state cooling of this mechanical object. So you can really bring them into the quantum regime and can start to do experiments. I could talk like really long about this because that's actually my main research. I will maybe focus on some things. So you can, by some, feedback control, so, you don't have to try to understand this in detail, but what you have here is in the bottom of this is, again, our particle trap with our parabolic mirror to focus the light. And then what we do is we actually capture the light, which is backscattered, and put it in a feedback loop, which is measuring the phase of, the oscillation, which carries information about the position of the particle. And then we can apply a so-called Kalman filter, a very clever filter, which knows about the dynamics of the system, and which is then helping us to cool this. And we were the first to show that can be used to cool the center of mass motion. Now people have used the same trick to cool to the ground state. So that is just, for people who like details on experiments, that is, by feedback, you can actually cool the center of mass motion of these objects. You can, I mentioned squeezing, so that is also, again, this phase space plot. So you start initially with a nice spherical distribution, which is what you expect from your harmonic oscillator. So if it's like a single state harmonic oscillator, you have just a circle in phase space. And if you have like a thermal state where you have different pairs of momentum and position, then you get, a distribution with some width. And if you then do certain manipulation, you can squeeze this initially spherical distribution, and you can also make like interesting spirals if you do some other stuff. And there's an interesting playing field. And what I just want to indicate here is that you can, by this feedback techniques, you can prepare nice motional states of these very massive objects. And if you also can cool to the ground state, you can actually generate interesting non-classical states of the motion of this big and massive objects. Okay, so let's go back to our question. So we want to test superposition principle. We want to test quantum mechanics. And what we think we have to do, in agreement with some people out there, is we have to increase the mass in this interferometry experiments and show that there is still superposition, or study if the wave function collapses, if there's like a universal effect, which at a given mass it is fundamentally impossible to generate such a superposition state. And here's our proposal. So it's called a Talbot nanoparticle interferometer. I gave it the name Natalie just because it's a nice name. And the idea is the following. So we start here at the top with our particle trap. So that is basically the stuff which I've shown you before in the slides. And then we release the particle, we pass it through a grating. So that's an optical grating, a laser grating, which acts as a, the generator of our superposition. And then we have a detector here where we detect the position of the particle. And then we have to repeat this experiment many times to get the statistical significance for interference pattern. And then hopefully we see an interference pattern as it's indicated here in this quantum curve. So the proposal is out there. We have, theoretically studied all the details, all the conditions where we have to conduct these experiments at, and we are building it now. So that is basically the project which is ongoing in Southampton as we speak. Okay, so now there is, I just wanted to mention this, it's an article which just appeared in Nature, and that is where we say, okay, so now if we want to really push these type of experiment to generate these very massive superposition states, what is actually limiting us on Earth? And what turns out to be the case is that it is actually gravity. Yeah, Earth's gravity is basically attracting, as we know, all the masses, and they fall down. So if you do an interferometry experiment, no matter in what orientation, so if you, let's say, shoot your atoms, molecules, or big masses in a horizontal direction, they will fall in gravity. And that fall basically limits, the time you can have for the evolution of the superposition state. Yeah? So just to give you an example, if I do this experiment, which I have just shown you on the previous slide, within 1 million atomic mass unit atoms, so I require something like 30 centimeters of drop distance, and I have sufficient time for the wave function to evolve so that I can see an interference pattern. If I wanted to do it within 10 to the 8 atomic mass units, so only 2 orders of magnitude more massive particle, then I already would need 1 kilometer. Yeah, and you can see that runs into technical difficulties. I'm not saying that some of my colleagues would not be brave enough to propose an experiment where you drop a single particle over a kilometer. But I think the more realistic way is to actually do it in space. And that is what this is about. So we have written this paper, which is based on, again, a 10-year-long development of our community. There's a proposal to do matter wave interferometry. So that is how it's called. If you have a massive particle, you put it in a superposition and you detect the interference pattern. So if you do a macroscopic superposition experiments in space, then what we have done here is we have basically explained what are the technological, and also societal, I cannot say that word. So what are the complications which society has to overcome to actually manage to do it? So it requires many people to be involved, and the space industry to help, and of course, lots of funding. So you see the price tag here, it's $1 billion. If someone has this money, we can test this in space in the next 5 or 10 years. Okay, good. So now let me change gears and talk about a very specific model which we test. And the reason why we have picked this model is because that is the one which is developed by far to the most detail. So there is a dynamical equation which basically describes in one consistent mathematical framework the collapse of the wave function, yeah, or which is, if you want, a solution to the measurement problem, because now you have this equation, you can see it here. It's a Schrödinger equation up to here, which is familiar, and then you have these ugly long terms, and I'm not going into details in explaining it, but what this model basically can do is it can work perfectly fine for small masses. So that is a mass-dependent CSL model, continuous spontaneous localization model, and that can, for small masses like atoms, it can explain that you see superpositions. If you increase the mass of this particle, if you go from an atom to a nanoparticle, the superposition gets destroyed by this effect, and the effect is modeled by a noise. So that is it's a white noise term which is introduced here, and now that is basically how this model solves the measurement problem. So the interesting thing from my point of view is, first, as an experimentalist, this model gives me a clear prediction. If you do this experiment at parameters x, y, and z, you know, collapse models predict you don't see a superposition state, while quantum mechanics tells me you should still see a superposition state. So that is something which I like a lot as an experimentalist, something which I can test. I do one experiment and I have two different predictions for different outcomes. And my experiment is just, you know, able to decide, you know, which one it is. What I also find interesting now, I have, you know, worked with these people who have developed these collapse models for quite some time, is that it gives you some hints in, you know, what this effect is. Yeah. So as you see the equation here, there's no physics in it. This is just a mathematical framework which describes random kicks which affect the wave function. So you start with the wave function with the quantum mechanical objects, and now there are kicks from the outside, which are these random kicks by this omega or by this W function, and they basically shrink the size of the wave function. So it's a continuous process. And at some point when the wave function is very small, you say, okay, for all practical purposes, it is collapsed. Yeah, so the collapse never really happens. And I had a discussion with Roger, and he doesn't like this at all. But you know, that is what these models do. What I find interesting is also that, you know, there are clear features of this noise, yeah, so which are needed to do the trick. Yeah, so you need the noise to be classical. You need this noise to be random. And of course, it has to break the linear evolution of the Schrödinger equation. That is why you do the whole thing, right? So, but now it is interesting that you have features for the noise which are required, and you can think about what could be the physics which is behind it. Yeah. So, for instance, something like a gravitational wave, which is classical and is also random. Yeah. So if you have your quantum system sitting somewhere here, and the gravitational wave from all sorts of sources which are outside coming in, then this quantum system would see those gravitational waves as a random classical noise. And in principle, I mean, if you put in the real features of gravitational wave from known sources, then they can unfortunately not do the trick, or at least we have not found the right way to do it, even on paper. But in principle, that is something which could explain this universal, you know, collapse of the wave function. Okay, so that was maybe all I want to say about these models. What they do is they predict two parameters. So RC, that is the localization length. So that is if you want, the correlation length of the noise. And there's lambda, which is the collapse rate. So how many of those collapse kicks you have per given time. So now you can plot these, and you get these exclusion plots. And that is what we're now using for experiments. And I will come back to this exclusion plot, which shows you lambda and RC. And you can compare experiment and this model in this nice graphical way. I come back to this when I have talked more about a specific type of experiment, which I'm doing now. So, okay, so the situation with this, with the testing superposition principle is this, that it is technically not the easiest experiment, as you can imagine, to put, you know, ever more massive, ever more bigger particles in superpositions. And they're very, you know, dynamic, very good groups working on this. So we thought about how can we, you know, test, you know, the superposition principle in a different way. Are there different experiments where we can test it? And there is one way, and but it only works again for a specific class of these predicted models, namely the CSL model. So now, what the idea is very simple. So you take for serious that there is a noise, a universal noise field out there, which is affecting all physical systems and which is collapsing your quantum states. And which is, you know, the explanation why we don't see macroscopic superpositions, for instance, in our everyday, you know, life and world. So now you ask the question, how can I test this noise field? And then it turns out there actually, you know, it's a large number of experiments where you can try to look at this noise. And again, because we have a background in optomechanics, we came up with this initial proposal in 2014. So you have a mechanical oscillator, it's a cantilever in this case, which is, you know, connected to a substrate, but it's also coupled to a light field in a cavity. And now you have this optomechanical coupling where you have a strong reading of the position of this mechanical oscillator in the light field. And now, of course, if there's noise affecting your mechanical oscillator, then that noise is mapped to the light field, and you can detect it very, precisely. And what we did in this paper with Mauro Padernostro and Angelo Bassi is we put in the noise from the CSL model, and we basically showed that if you then look at your resonance, so I showed you this frequency feature of the mechanical resonator. So what you should see is a heating effect. So you should see a broadening of the feature of the resonance feature in the frequency domain, and that's the effect. Then it all went very quickly, so that it turned out there was an experiment done in Tjerk Oosterkamp's group in Leiden. So Dirk Baumeister knows him very well, and they do these magnetic force resonance experiments. They have cantilevers with permanent magnets attached to it, and they hoover them at very low temperature, 10 millikelvin and less, over a surface to measure single spins which are interacting with this magnet. And now what they also had done by doing this experiment is actually probing for that noise without doing this, and that was the first bound which came from mechanical oscillators to test collapse models. And then we have done some updates and some more detailed experiments with layered masses, and I will not go into details, but now here you see already basically a good part of this parameter space of the CSL model, which has been excluded because we didn't see the noise. And some models which have been predicted by Stephen Adler are now more or less fully excluded. So there's no collapse noise, there's no collapse in this parameter range, which is predicted by Stephen for a specific setting of lambda and RC. Okay, good. So now there is a tech project. I should maybe advertise this briefly, which is a European collaborative project, which is hosted at Southampton and across Europe, 9 partners. So we are building basically the next step of this noise measurement experiment based on mechanical oscillators. And what we want to do is we want to trap a levitated particle. So the test before by Tjerk's group was done with the cantilever, and we know that from just the mechanical properties, the clamping, the cantilever clamping, gives some limitations on the quality factor. So that's also not entirely true anymore, because people can do very sophisticated things in nanofabrication and can also get very high quality factor resonators. So quality factor means is you excite the vibration, and it vibrates or oscillates for a very long time without decaying. But if you do levitated particles, if you use these little particles in traps, this is a Paul trap here, which uses electrical fields, then you can reach much higher quality factors, and that's what we do. So we put it in an absorption helium-3 cryostat. So that's an experiment which is running for another year, and we have all the components together. We now put them in our fridge here in Southampton, and we try to do this experiment. So now I come back to this exclusion plot. So what you see here, the orange part is what has been excluded by cantilever experiments. So I showed you that with this layered mass, you can also cut through this Adler model a little bit. The black line here is what we want to do in tech. What is very interesting is that you can also actually use many other mechanical oscillators, including those where people have spent a lot of time to understand all the noises, and that is gravitational wave detectors. So in LIGO and Virgo and these big kilometer-long gravitational wave detectors, of course, you also have a mirror, an end mirror in the Michelson interferometer. We will hear about this layout much more in Dirk's talk, I think, in a couple of minutes, if I find an end point of this talk here. So if you have this end mirror in the Michelson interferometer, and you have your laser beam as you have in the Michelson, then of course you measure the displacement of the end mirror, and they have in LIGO they have done this to perfection, and you have a big mass. You can ask for the noise and the heating in those mirrors, and if you do this, then it cuts out a big part of the parameter space, which is the green path. The green part that also applies to LISA Pathfinder. So that was this the space experiment Yvette mentioned, the LISA mission, which is now going ahead with the European Space Agency and NASA to have basically a space-based gravitational wave detector. And LISA Pathfinder was this mission where they had like two kilogram cubes in the satellite already up there, where they stabilized basically the position of these two masses to an incredible precision. So they measured very small accelerations affecting the center of mass motion of these two masses, and that also was an instrument which is sensitive to this noise prediction, and that also contributed to cutting out this year. Then there's X-rays, the famous Gran Sasso experiment, so gamma X-ray emission from germanium, pure germanium samples. So I will not go into this here, but these experiments, they cut out a different part of this fraction. You see there's still some parameter space to go, and that is, by the way, the initial prediction from Ghirardi, Rimini, Weber, which started off this collapse model discussions beside Philip Pearl, of course, who was a main contributor, or if not even the inventor of the CSL model. Okay, good. So that is, I don't know how I'm doing in time. I lost some of the time.
So actually you're down to about 15 minutes total, but it would be great if you could finish in 10.
Okay, good.
You might allow a couple of quick comments before then.
Okay, so then I just mentioned in passing that we do this magnetic levitation experiments, which are very similar to the optical ones, but here we use superconducting type 1 LED objects to use the Meissner effect to levitate permanent magnets. That turns out to be incredible accelerometers, so devices which are sensitive to measure accelerations. And again, they're very interesting for measuring CSL noise, but they're also interesting for measuring tiny forces, for instance, gravity. So there's a proposal which I maybe want to mention a little bit. So the idea is to levitate 2 of those magnets. So now these are bigger. They have a diameter of roughly 10 micrometer in diameter, and you trap 2, and you do like a very primitive version of a Cavendish experiment. So it is not using torsion pendulums, but you have basically one mass, which is the so-called source mass. It generates, if you want, in a classical picture, a gravitational field, and then you have the second mass, which is the probe mass, and that is now trying to measure that field. And the aim is, there are also others who have started this and who have done very impressive experiments. So Markus Aspelmeyer's group in Vienna. So the aim is to actually push down to a mass regime which has not yet been covered by gravity measurements. So where no one has ever measured what is actually the gravity of a mass which is less than 1 milligram. Yeah? So no one knows. Yeah? And so that is interesting. There may be not precise expectations what will happen, but I can show you a graph which maybe explains why that is interesting. So what you see here, also Markus Aspelmeyer has a similar plot, which he always shows. So that is simply a mass scale. So here are small masses, here are neutrons, atoms, molecules. And on the other hand, there are like big masses on the right-hand side. So that is where, big experiments like LIGO and LISA Pathfinder are. And so in the blue region here, that is where we know about gravity. We can measure gravity. We have, detected the gravitational field or the gravitational effect of masses. Now, Markus has the new record down to milligram, 2 or 3 milligram masses. On the other side here, the red part is where we have systems in quantum states, where we can do superposition experiments. So I told you about Markus Arndt's experiment. That is here. So that was maybe 5 years ago when they did a 2000 atomic mass unit particle, which was in superposition here. So now they moved a little bit towards here. And then you see here that region in the middle, that is not discovered by quantum experiments, but also not by gravity experiments. And that is where we want to push basically with our experiments. We want to increase the mass for the quantum states, and we want to decrease the mass for the gravity experiments. And then hopefully at some point, we meet in the middle and we can do an experiment where we have both at the same time. And then the hope is that, new physics will show up, and we can also test what is actually the gravity doing in a superposition. So there are some ideas. I maybe mentioned this also briefly. I think that is from at least writing down equations, that is closest to to Roger's idea of the gravitational state reduction. So that is the Schrödinger-Newton model, which is a semi-classical model. So you can start, for instance, from Einstein equations, and then you use just, brute force, and you put into the energy momentum. So the source part of these equations, you put in the expectation values for your system, and you can then start calculating and deriving and making lots of assumptions. You can boil it down to a dynamical equation for your quantum system, which is again the Schrödinger equation, which now has this gravity terms there too. So one is an external mass, so that is how the superposition would interact with an external mass. So that is where all of these atom interferometry experiments are, where you measure Cow phases and these kind of things. So you always have like a big mass sitting here, and you use your atom interferometer to probe this external the mass effect or the gravity of this external mass. But there's also the second one, so that is the self-gravity, which is similar to what Yvette has mentioned in her talk. So that is really, take the assumption you have the superposition, and the superposition, the wave function, which is in superposition, is not only really, like an, I don't know, a probability amplitude of, expectation, where the particle is, but it is also something like a mass distribution. Then you have like a gravitational effect, which is affecting your system by gravity and self-interacting. So the experiment you want to do to test this is actually to prepare, a very massive object in a quantum state, and then you let evolve it, and quantum mechanics will tell you that it spreads, the wave function will spread, it will diverge. But the Newtonian part in this Schrödinger-Newton equation would actually try to contract to because it's an attractive force, it would try to shrink the size of the wave function. And that is something which you can study if you put in numbers. And if you really wanted to do that experiment, it turns out, again, you have to do it in space, because for large masses, it takes incredibly long for these effects to show up. So the timescales are not in favor. So we came up with another idea, that is with André Grossart, who is the only person I know who is really, working on the Schrödinger-Newton models, and is taking it seriously. And he's not so much worried about that they, allow for faster than light signaling, so that they're not exactly in agreement with what we would expect from quantum mechanics. So André is relaxed about it, and he thinks that can be solved in a different way. But together with him, we basically predicted that there should be an effect on harmonic oscillators, namely a shift of these energy states. So if you can now, people can do it, as I told you, cool to the quantum ground state of a massive mechanical oscillator, then you expect, if you basically excite to the first, second, and so on excited states, that there's a shift in this energy level. So you should see a shift in the frequency of your resonator compared to the non-Newtonian case. Okay, so I maybe should stop here now. There was the other interesting thing about gravity, which also is somehow related to what Yvette mentioned. So now here, again, the idea is to probe into how does actually the gravitational field of a superposition look like? And in terms of space-times, you can put it in that question, is it possible to generate a superposition of space-time itself, so that, as it's indicated here on the left-hand side. I know my time is up. Let me just finish the slide, and I will stop. We know Roger would say, yeah, it is possible. If the mass is small, then everything should be fine. But if the mass is too big, then at some point space-time is unhappy, and it's maybe collapsing in one or the other option. So now again, here's an experiment where we actually want to probe: is it possible to detect if there is such a superposition of space-time at all? And the idea is the following: that again, you have two predictions. So if space-time, if gravity is quantum and space-time, then that means, which are a lot of assumptions, I'm fully aware. So let's say gravity is quantum, and that means that space-time can be in superposition. Then if you do a two-mass experiment, so one where you have a superposition, and the second where you probe basically the superposition of the first, then the result of the experiment of your quantum experiment should be this here. It should be like in a double slit experiment. So you statistically probe, it collapses into the left or the right-hand side. So you get this, distribution which looks like this. If gravity is classical, so if there's no superposition of space-time, then in the same experiment, you would get a completely different outcome, because then what that would mean is that, also, your superposition is a mass distribution. And that means that your probe system is, just passing through, because it would be attractive in a perfectly symmetric way setup. It would be attracted in the same way to both systems, so it's not affected. So the outcome of this experiment would be a completely different distribution in the outcome of your measurement. And I stop here. There are many more ideas. There's no time to talk about it, maybe later. Sorry, I think I have already taken more time than I should have.
Well, thank you very much indeed, Hendrik, for a very interesting and clear and stimulating talk. There's a lot more that can be said. It turns out that you have, I think, 5 minutes left in the allotted time, and so we do have time for some questions, and I've got some. There are some that have appeared on the Q&A. These are main Q&A, and I think these are. I'm looking for ones that pertain to your talk, which that actually they've only just come through. All right, so they've actually just arrived. So there's one for Yvette, but okay. So I've got one here from Abdelataj Abu Jude. An important element gradient in the measurement issue. I think this is by the timing directed at you. An important element gradient in the measurement issue is the non-local, which you cannot ignore. Of course, even deal with successfully. The non-local is essentially, dear quantum physicists, including you, with respect, how would you describe the state of superposition in a non-local way? So that's the question, and obviously it's a very large question, but so, give you the chance to give your perspective in that way.
Yes, okay, so of course, there could be a lengthy discussion about non-locality, which
yes,
I would try to avoid at this point. Maybe we can talk about this later. My answer would be very simple. I would say, a spatial superposition state is the prime example of a non-local state, right? It simply means that, the particle, in this kind of configuration is not pinned to one location. If you use the wave function as we do in quantum mechanics, then there is no surprise, and it means we can have, after the measurement, the particle in two locations. So, some people would say that if you do these interferometry experiments, you actually probe, the non-locality of these particle wave things. Yeah.
Okay, thanks, George. I'm only just getting some more questions, which I'm not. I'll just let me just try one, Chairman's prerogative, and
sure.
Say there's a sort of class of who we say hard theoretical physicists who have a view that's rather different from that's perhaps being exercised here, who would say that, for example, the Aspect et al. Experiment demonstrating Bell inequalities was not worth doing because the outcome was perfectly well known, and we understand quantum mechanics, gravity is a metric which is waiting to be quantized, and so on and so forth. Which of the experiments that you and perhaps the last speaker have described would you say are the ones that they would have the most, that tribe, if you like, would have the most doubts about predicting the outcome?
Okay, so let me try to speak in their name.
I wasn't mentioning names. Yeah.
I mean, of course. So I think if you think that everything is fine with quantum mechanics, then of course you assume that there's also no fundamental issue in generating larger and larger and more massive superpositions, right? So I think they would not be surprised if that can be done, and that is indeed a comment which I get all the time. That you know, there are of course, you know, so-called decoherence mechanisms where the quantum system is interacting with the environment, and as soon as you can turn off those, you can still perfectly generate a superposition state. So that is the expectation from standard quantum mechanics. And I mean, you know, I think this is one of these things. If he could find something, yeah, which is deviating from this, just for the sake of showing it to them, I'm totally up for doing it.
But the question was, which of these experiments would they actually have pause about anticipating the outcome?
They would have what about?
Would they not be able to anticipate the outcome? Are there any of them that you would say they would not anticipate the outcome?
No, I think they would not anticipate that it is impossible to generate superpositions, right? So they would not anticipate to see, you know, for like a universal, for a general reason, to not see, you know, superposition states. Yeah.
Oh, okay. Well, thank you again very much indeed, Hendrik, for a lovely talk. With now it's spot on 10:30. Let's move with Dirk Boomeister of the University of California at Santa Barbara and Leiden University. He's going to tell us about an experimental investigation of the reduction of the quantum wave function.
So yes, it's indeed a great pleasure to participate in this conference for Roger Penrose, his 90th birthday and the celebration of the Nobel Prize. I was lucky enough to participate in his 64th birthday party, which was actually a huge birthday party because he didn't like 65. He thought 64 was a much more beautiful number to celebrate as a mathematician. So I actually was a postdoc with Roger Penrose working a little bit on twistor theory and whether there was a relation to special light fields. And at that time, I just enjoyed learning about his theory on twistor theory. And I think that theory is underlying basically all the work that we are talking about the coming or these days, but there is not a particular talk about twistor theory itself. So I put a few little things on one slide that I've been intrigued by. So this is this beautiful picture that Roger made, a famous picture. And you see these lines that are linked to each other and lie on nested tori. And it turns out that those are sort of the most elementary solutions you would find for light and for gravitational radiation in the linearized case, or if you work in the language of twistor theory. So we tend to use coordinates in which you use plane waves as your standard waves, and they are utterly unphysical because they extend from plus to minus infinite. Energy is not localized. Whereas in twistor theory, the most elementary states, or the elementary states as Roger calls them, are actually localized energy solutions that propagate with the speed of light. And here at the bottom, there are a few references to works that we did based on twistor theory related to special knotted structures of light, of gravitational radiation, and also of plasma. Because if you start with a linked magnetic field configuration, you would get partly self-stabilizing plasma configurations. And I'm 100% convinced that we hear a lot more about these things in the coming 20, 30 years. And I'm sure that Roger deserves another Nobel Prize for the twistor theory. So that about twistor theory. Let me then move to the second time I went to Oxford. So the first time I was just enjoying the theory environment in the mathematics department in Oxford. Then I came back to Oxford a few years later and started a quantum optics group based on entangled photons and the like. And Roger Penrose literally came to us and they said, you have to do this experiment that I have in mind. And it was an experiment with photons bouncing off satellites, and he had it all figured out. And he even had a student who was going to help him doing that. And that's the guy here on the left. It's Will Marshall. He was obsessed about space exploration. And and here is Christoph Simon. He's a professor now at Calgary. And we came up with an experiment because I said, fine to think about an experiment in space. And in the end, I think Roger is going to be probably right that there might be experiments like he envisioned to happen in space. But I said, let's see what we can do on an optical table. Let's see how far we can push creating superpositions on an optical table rather than going out in space. And so this is Christoph Simon, a theorist. And then we came up with a plan of how to create superpositions of a mirror and then eventually analyze the decoherence of such a mirror superposition and try to make conclusions about whether or not these extra decoherence mechanisms that Roger is after are really there. And I should say that Will Marshall, he now actually has about 200 satellites out in space, because after he finished his PhD, he started working for NASA, and he realized that his cell phone was more powerful than the electronics that are on the regular satellites. So he developed satellites based on cell phone technology communication systems. And now his company, Planet Lab, is making full images of the entire world every day. So you can basically count every tree every day. You can do marvelous things with that. So I just want to mention that there's a lot of spin-off from the ideas that Roger Penrose had and pushes a lot of people to push the technology. So, but let's go back to the very basics of what we are after. What is the collapse of the wave function? Is it real? Is it an illusion? And there are many ways of think about that. And I think it's still open what will be the final answer. And therefore it's important to push experiments and see what really happens, because only then we can make conclusions. As everyone knows, Bohr was more of the opinion that the wave function describes what we know about the system. And if you obtain more information, then instantaneously our knowledge changes, and that therefore the wave function also instantaneously changes, and therefore you don't have to be too much concerned about non-local effects and the like. It's just representing what we know about the system. Then the other end of the spectrum is that we consider the wave function as very realistic. And if the wave function is describing a superposition, then there is a true superposition in the universe of that system. Then there is what is called environmental induced decoherence. And I think that's the more standard way of describing what happens during a measurement. And in that way, you would find that on extremely short timescales, any quantum superposition with a significant mass will simply become identical to a system that we have to describe with probabilities for particular outcomes. So the loss of information or the entanglement to the environment, and then the loss of the information in the environment, will basically cause the system that we analyze to behave as a pure classical system with probabilistic outcomes. And I think most of the people will follow this assumption or this point of view, and expect that the harder we work to get larger and larger objects in superpositions, by isolating them better from the environment, that we will prove that such superpositions simply persist even for larger and larger objects. So you really have to understand very well what environmental induced decoherence tells you before you can look at anything on top of that. So very, very briefly, von Neumann postulated these probabilistic outcomes. You have a quantum system interacting with an apparatus, and somehow the apparatus is designed to read out certain things. So there's a preferred basis. You ask specific information from your quantum system, and you can take the basis that corresponds to your observables of your apparatus. And in that basis, you have this form of interaction. And then if you start in some quantum superposition with complex coefficient Cn, you start with your apparatus in a well-defined initial state. Then as a result of this interaction, you get a system of apparatus and quantum system described by this entangled quantum state. And then it's a postulate that the probability to get different outcomes here is the absolute value squared of Cn. So that is von Neumann's postulate, and you still find it in many textbooks in quantum mechanics. And that's, of course, where the mystery comes from. How do we get these probabilities? Now, environmental induced decoherence makes this system bigger. It says the states of the apparatus are coupled to the state of the environment. You do the same part. You take the environment initially in a well-defined state, but then due to interaction with the environment, you get entanglement of your quantum system, apparatus, and environment. And then you take the trace over the degrees of freedom in the environment. And that's the trick. By taking the trace, you basically get a reduced density matrix. And I will, because I know not everyone is an expert in this in the audience, I will give a very simple example. The reduced density matrix of the remaining system behaves like a classical probability distribution with Cn squared coefficients. So let's quickly make sure we understand this argument in detail. So this is a trivial slide. Just if you have a quantum two-level system with alpha and beta, your complex coefficients, then your density matrix in, say, the 0, 1 basis is defined here. You take the state and the conjugate state, and then this density matrix of this pure system has this form where on the diagonal elements you have your alpha squared and beta squared, and on the off-diagonal elements you have the coherences that makes it a pure quantum state. So that makes that you have you can have interference between the two states if you were to do an experiment. Now, in general, the density matrix is a bit more powerful than just this wave function, because you can indeed describe mixed states, classical mixed states that are in classical probability distribution states by just having the sum of I, Pi is 1, where Pi is the probability to be in a particular quantum state. And if you only have one, if you have a pure quantum state, then there's only one of those that is 1. Otherwise, you have different values. So here you have a mixed state. So on the diagonal, it looks the same here, but the off diagonal are 0. And this would be a classical mixed state with coefficients alpha squared and beta squared. So now let's see if we take this two-level system and we interact it with another two-level system so that we start with an entangled system. So we have system A and B. They are entangled, so you cannot write it as a product state of the quantum state of A and the quantum state of B. And this is a particular example of an entangled state. And the density matrix of this state is just as defined, psi AB and the complex conjugate state. And now if I take the trace over system B, that means I just sandwich this density matrix between the states of system B, and I sum over all the possible states for system B. In this case, there are only 2 for state 0 and 1. So let's do that. Let's take this entangled state and take the trace over system B. So we have B0 state on the left and the right here, and the density matrix in between here, plus it's the summation over these, plus the state beta system B in state 1, left and right you sandwiches. And it's clear that if we start in an equal superposition of 1 over square root 2, you get twice 1 over square root 2 in front, it's a half. And then if you sandwich between 0 for state B, this state gives you 0, this state gives you 1 with this coefficient, and here on this side you get this state with the complex conjugate phase factor in this, and you simply get as final outcome a half system A in state 1 plus a half system A in state 0. So by entanglement with this other system and tracing out over the state of this other system, your reduced density matrix of your quantum system looks identical to a classical probabilistic state. And that's all that happens, according to many people, when you couple a small quantum system to a larger detector apparatus that includes the environment. So now you see that indeed the reduced density matrix of a pure quantum system, where you trace out over the degrees of freedom of the environment that got entangled through the interaction with the system, the reduced density matrix is precisely a classical probability distribution. So how can the apparatus determine the basis in which you look at it? Well, let's take a single photon that comes in on a beam splitter. It can go left or straight through with a 50% probability. If I put my detector and environment here and there, and the detector often is a combination of detector and environment. What happens here in a detector is one photon goes in, it accelerates, it releases one electron that is accelerated, it collides with more electrons, and you get a whole bunch of electrons. And at that moment, it's already too large to ever do an experiment where you interfere all those electrons with all the electrons being activated here. So in this basis, you project out onto the photon being here or there. Instead of a single photon detector where you have this avalanche of electrons and giving a click, sound waves, and so forth, if you were to use a single atom that would absorb the photon, then you could think of doing another experiment by using the emission of that photon from that atom and do an interference experiment. So it's all a matter of whether or not you lose the possibility to have control of all the degrees of freedom in your larger system. So we call something a detector because it couples to the environment, and therefore we can no longer do an interference experiment afterwards. If I change my apparatus, I can also look at the different bases, say the photon being in superposition of here plus there and here minus there. I just include in my detection apparatus another beam splitter, and then a click here projects out onto a superposition of here plus there, the photon, and this one with a minus sign. So also an interference experiment in this particular way, you prove interference by getting a unique outcome. So you always learn about interference and superpositions by getting precise outcomes in a well-defined experiment. So in that sense, you never observe a superposition directly. It's always an indirect measurement, and you have to design your apparatus such that you look at what you are interested in. Okay, this idea of environmental induced decoherence is very well developed, and in particular Zurek and Unruh, they're a whole tradition of theorists that have investigated environmental induced decoherence. And here you would see what happens if you start with a piece of material in a superposition of two places, initially prepared. Let's assume we can prepare it in a quantum superposition of being in two places. So your density matrix will have off-diagonal elements and diagonal elements. You can then do a precise quantum calculation, including the tracing over the environment. So you have to specify how you interact with your system. And in many cases, you interact with a position-dependent term. Think of particles or radiation probing a certain region. So if you do that theory, then the reduced density matrix of your quantum system that you're interested in, after you've traced out over the degrees of freedom of the environment, has this general form, where you have the standard unperturbed quantum evolution plus terms by which you have decoherence both of the diagonal elements and the off-diagonal elements. Now, these terms, they decohere by x minus x prime, and in this particular term, x minus x prime squared. So this is the dominant term, and only if you start in your density matrix with two different positions, x and x prime, so if you consider the parts that really are central to the displaced positions, only then you get this term being non-zero. So that means that the off-diagonal elements, which contain x and x prime, they are the ones who will experience these terms predominantly. And therefore, after a very brief amount of time, this will be the dominant decoherence term, and it will just push down the off-diagonal elements, and you're left with a system that might still be in a superposition, but you will never be able to prove that it's in a superposition because the density matrix is just the same as a classical statistical distribution. So this is the typical quantum mechanical decoherence equation, and it scales with delta x squared. And in this case, it's position, but depending on your interaction, it could be something else. It scales with temperature, mass, and so forth. So this is what you have to understand very well before you understand anything on top of that. So looking at this equation, if you were to take some larger mass, somehow I have something covering my text. I cannot quite read it, but it's a room temperature. I don't know what it was, 1 gram mass, I suppose, with a superposition of 1 centimeter. If you were to try to create that, then the decoherence of the off-diagonal elements compared to the diagonal elements will be 10 to the 40 times quicker. So there will never ever be a way you can observe such large superpositions according to this interaction mechanism. If you look for an electron with a tiny, tiny mass over tiny, tiny displacements, then you can have that the off-diagonal elements survive for a long time. And then you can perform an experiment by which you prove that you can have a superposition by combining paths on a beam splitter type. And it's precisely the study of this decoherence mechanism that were done by the heroic experiments by Serge Haroche and Dave Weinand. And during the announcement or during the ceremony, those two experiments that demonstrated this decoherence were sort of the crowning experiments. So I won't go into it, but Haroche, they had prepared a 10 photon state here in a cavity and then got atoms, Rydberg atoms interacting with this. And by the interaction, whether the atom is in the ground state or the excited state, you get different phases on these 10 photon states. And that's your superposition, your large superposition, 10 photons being in one state or the other. And that's then your measure, your distance measure D. And what they showed is indeed that the coherence between the two states decoheres according to this distance squared. And it's important to realize that those 10 photons, the loss rate of these photons is much, much smaller than the decoherence rates. As I showed before, the decoherence dies off very quickly. So it's not that one photon of those 10 left the cavity and got detected and you can measure something that destroys the quantum state. It's just the fact that there is some leakage. Even if you still have your 10 photons in the cavity, the system will very rapidly decohere and you will no longer be able to prove that you have a superposition of those two different 10 photon states that are phase displaced. Now, Haroche did those experiments with atoms and Weinand did experiments with ions, where the interaction with the environment is controlled by electrodes. So they were able to introduce different types of environment, and then your delta X, the distance that is essential for the decoherence rate, can depend on different parameters, and that's what they showed. So I'm not going to go into detail, but the conclusion from those experiments is basically that the collapse is the result of unitary quantum evolution of the entire system, and basically leads to a reduced density matrix that mathematically has the same form as a classical probability distribution. And again, many people are perfectly happy with this distribution, with this description, and the description is pretty advanced and needs a lot of detail to understand. Okay, so even if the wave function of the universe is a single entity, for us as an experimentalist, you decide this is my quantum system and this is my environment. And then in that case, you can talk about the collapse of the wave function. Of course, on the whole scale of the universe, you will not be able to do that, but you're dealing with superpositions that cannot be interfered anymore and therefore cannot be observed. So therefore, it's perfectly consistent with our reality. And people might call this many worlds. And I always like to show Lev Weidman. He came up with a patent. Long story short, I don't think he could file it because people did not understand his concept well enough, but maybe by now it's a long time ago. But basically a little watch, a single photon, a beam splitter, 2 single photon detectors. And if you have a difficult decision to make in life, you just ask your watch what to do. If this one clicks, just do it. If this one clicks, don't do it. If it goes wrong in one or the other cases, you might have some peace of mind that in another realization of which we are completely disconnected, you did the right thing. Any objections? Well, now we finally come to Roger, of course. He says, you should be very careful in pushing results of quantum mechanics in the regime where gravity, general relativity starts playing a role. And the idea is fairly simple. If you have a mass in one place, it determines your space-time structure. If the mass is in a different location, and of course, this only is if makes any sense if there is some other surrounding, some experimental setting that sets certain boundaries, then you can talk about different positions of a single mass. And then close to those masses, you will have a slightly different space-time structure. And as a result, you cannot just write down Schrödinger's equation for superposition because there is no unique d by dt defined. There is no unique space-time structure defined. And then the way to estimate what goes wrong, the most obvious thing to do, and that is why I think several people came up with the same equation, but with different arguments. You look for the difference if the mass is in one place on a test particle compared to if the mass is in a different place on the test, the force is on a test particle. And then what else is more natural than to take the difference, take it squared, because you want to get something positive out, no matter what these fields are, and then integrate it over space. And then to get the units right of an energy, you have to divide by G. And then I think Roger sometimes tends to say, I'm not quite sure about this factor 4 pi, but that's the typical thing you use when you write down this type of energy. So this is a very natural way to describe how much space-time is not characterized by a single space-time structure. And it's expressed in units of energy. And therefore, if you force a system in such a superposition, and I think Roger also likes to call it a blister of space-time, you sort of get an energy uncertainty of this order. And then you use wave mechanics or quantum mechanics, delta E, delta T is of the order of h bar to get a lifetime associated to such a superposition. Now, there are many, many things one could argue against such an equation. For example, if you talk about the superposition of an electron, you definitely will never do such a calculation, because if you take an electron in a superposition and you were to calculate the difference of electron interactions with a test particle, this expression would be extremely large because the forces are much stronger. And that would imply that you would never be able to get electrons in superpositions. And then, of course, the argument is, well, gravity is really a very different beast from quantum electrodynamics. So perhaps it's still fine to do something of this sort. Okay, so back to the second time I was in Oxford and Roger suggesting to do an experiment. So since then, I basically devoted a significant part of my life to do such an experiment, and I will guide you through it very quickly, maybe another 15 minutes. You can calculate for a specific mass distribution what this gravitational self-energy is. You have to take into account that your material is made out of little pieces of matter. It's not just a uniform piece of material, it consists of atoms. And actually the atoms consist basically of nuclei. And the nuclei actually consists of quarks, but then most of the energy is in the gluons. And therefore the size of the nucleus is probably a good way to estimate the location of the energy of the mass of a piece of material. You just need to know where the atoms are. So for Roger Penrose's prediction, it is important that you make a superposition where the displacement is of the order of 2 times the size of the mass. And here, this A is the important parameter. What is the size of the mass actually for a piece of material? And this effect, it's quite interesting that if you displace it by 2A, you basically already have the most of the effect. If you just extend it further to infinite, it doesn't really change the decoherence rate much, maybe a factor of 2. So it's a very specific distance dependence that follows from this model. And that distance dependence is very different from other predictions that are based on fluctuating vacuum and the like, which typically scales with delta x and not in this particular, or linear in delta x or in delta x squared. Okay, so, well, I'm from the optics field, so what can we do? We can look at the tiny mirror on some mechanical system and try to use superpositions of photons to bounce off these mirrors and try to create superpositions of mirrors. Very naive, but you have to start somewhere. So for the calculation, again, what is the mass and where is the mass located? If we take the material to consist of atoms, and the atoms basically have the mass in the nuclei, where the nuclei can be seen as a little ball of energy, then you can take A, the size of the mass distribution, to be 10 to the minus 15 meters. And then for objects of this shape and on the mechanical frequency of kilohertz, you will find that you get, according to Penrose, decoherence times of 1 millisecond. There are many things that make these parameters very hard, especially here that we assume that the interaction with a single photon can cause enough displacement to get to this delta x of 2A. And that sets very strong requirements on the optical cavities that interact with such a mirror. So there are many hidden assumptions in these parameters. Apart from taking the nuclear size, you could take the size of the quantum ground state wave function of the entire mirror. And that is much larger, 10 to the minus 13 meters. And then because A is larger, you have to displace it more. So the decoherence times by this mechanism becomes longer and longer. They were already mentioned, if you look at these experiments that Marcus Arndt performed and is still performing initially on C60 molecules, there you find that the decoherence time with such a calculation will be 10 to the 10 seconds, the Penrose decoherence time, which will be way, way longer than the standard environmental induced decoherence time. So that is the task, make the environmental induced decoherence time longer than the Penrose decoherence time. And that's a challenge. We initially proposed an experiment with a single photon going into a superposition, either in a fixed cavity or a cavity with one moving mirror. And then by measuring the properties of the photon leaking out of this system, you can prove whether or not there was a superposition in these cavities again by doing many, many measurements. You have to repeat these experiments many, many times and then look at the statistics, look in different bases, and then you can prove that indeed such a mirror would have been in a superposition. Now, just about optomechanics, it's a very simple interaction for an optomechanical system with one mechanical mode, a cavity with photons, and an interaction where the photon bounces off the mirror and displaces. So the Hamiltonian is of this form. You have the number of photons times the energy of the photons. You have the number of phonons, the mechanical excitations in your mechanical system that holds the mirror, times the frequency, h bar of that mechanical motion. And you have a coupling term, which is very easy derived by just seeing that you displace the mirror a tiny bit by the number of photons you have in the cavity. And then if you take L over L plus X, where X would be the displacement, it looks, it's approximated by 1 minus X over L, where X is the position corresponding to the phonons, and position operator is of this form. So with those two little steps, you would precisely understand this coupling term. So optomechanics is the way I went, and that's my field, but there are many, many other ways of trying to get larger and larger objects in superpositions. Just for the record, optomechanics is at least as old as 1577, or at least the understanding that optomechanics exists. And these are drawings by Brahe. And those drawings luckily came to Kepler, and he noticed that the tail of the comet, the Great Comet of 1577, which Kepler saw with his own eyes, the tail is pointing away from the sun. You see here the Earth, the sun is nicely moving around the Earth as it should be in 1577. Then you see the comet going around the sun and the tail pointing away from the sun. So from this drawing, Kepler concluded that the sunlight could push things away, radiation pressure. So that's what we're using. Now, if you have an optomechanical system, you can calculate precisely how your phonons can leak out to the environment, and there comes the coupling to the environment. And you have to analyze that in detail, and you will always end up with an equation similar to what I showed you before. So that will give you the environmental induced decoherence time. And yes, we did all kinds of calculations, and we thought it would be acceptable to start an experiment, knowing that we would have a lot of hurdles to overcome. So the initial parameters were a 10 kilohertz system, a cantilever temperature of 1 microkelvin, because this environmental induced decoherence scales with temperature. So you have to get the mechanical mode to very low temperatures. And for that, we have to use the same tricks as atom people use to cool down their atoms. You have to do sideband cooling, so you can suck out phonons from such a system so that you can cool it below the temperature of the environment. The environment determines how much phonons can leak through to the rest of the apparatus. So the environment also has to be at low temperatures, but not at microkelvins. Okay. So I already mentioned optical cooling. If you have an optical cavity mode, you have a mechanical frequency. If I take a laser beam and I put it on the red side, on the lower frequency side of the cavity resonance, then with the absorption of a phonon, the photon becomes resonant with the cavity. And therefore you have a resonant enhanced process by which phonons are going to higher frequencies by absorbing photons. And that's called this sideband cooling. And by that you can take out phonons from a mechanical resonator. Everything has to work.
Hendrik, can I just, excuse me,
Yes.
Dirk, can I just interrupt and say you have 5 minutes left of your allotted time?
Okay, I'll have to speed up a little bit. So we have a lot of developments in the optomechanical systems. And now we'll go to the latest systems. We have to work at extremely low temperatures, base temperatures. On top of that, do optical cooling. So we're working with a large dilution refrigerator. There's even some nuclear magnetic demagnetization states to go to temperatures lower than 1 millikelvin, but we also have to fight optical heating because the experiments are done with light. So any absorption will heat more than we can cool. So we are not yet using the nuclear demagnetization states because we're not at such low temperatures yet. This gives you a better idea of the size of the apparatus. This cryostat is developed to have very low vibrations. So there are very few cryostats in the world that are actually hanging from springs. And there are these eddy current dampers. You see here 2 of those. I think here's a better one. They are just are very strong permanent magnets between copper, and if they move, they create some eddy currents, and those currents are dissipating and doing the damping. Then we developed a mass spring system using electronics, the analogy with electronic filters, so that we can filter out precisely the frequencies that are still passing through the cryostat. And then we wrote some nice little paper on that. And then at the bottom of this, we put our optics experiment. In this case, it contains a cavity with this tiny mirror, and it has 9 low temperature compatible motors. And actually the company, we developed those with Jensen Precision Electronics, and that company is now supplying these type of motors to, I don't know, hundreds of groups in the world. So it was a very nice development to be able to move things. And then once they are in the right place, you don't have piezo's on that could cause noise. So these motors move in little steps, and once they're in the right position, you don't touch them anymore. Then there was a lot of development on these optomechanical systems. Here you see tiny mirrors with the same coatings that are used for LIGO. The diameter is the size of a hair. Then to have vibration damping on chip as well, we put a large mass around it, again on mechanical springs. So you get, again, some optical damping. We can do optical cooling, and without this extra damping, we got a lot of noise in our system. But with this extra damping, we got very clean mechanical resonances. Here we did some optical cooling, going from room temperature down to 23 millikelvin just by optically taking out the phonons. Here we did some experiments starting at 5 Kelvin and still being able to cool further down. But if we start at 100 millikelvin, we come into a regime where we have some optical heating. So we run into several problems, and we decided to switch strategy. And the new strategy is not to use single photons anymore, by which we put a superposition, but we're going to use 2 mechanical modes that we couple through light for some initial time. Then we let the system on its own. You have entanglement between the mirrors, and then you probe that entanglement. We did experiments with 2 of these mechanical modes so that you can create, you can transfer the state from one or the other, or create a state that is a superposition of the 2 states. And you use the same mechanism as the optical cooling. You can take a laser here. You start with an empty cavity. you go from an empty cavity to one photon in the cavity. One laser photon is scattered into the cavity by exciting one phonon in the mode. So M mechanical mode 1 will, sorry, let's see. Oh, sorry, yes, no, it's the optical cooling. We take out one phonon from mode 1, and then we can do another scattering and take the photon out of the cavity and put it into the other phonon mode. So we can swap the state of one mechanical resonator to the other. And we did that with a sample where we had a reflecting membrane and a mirror in a cavity. And then with that system, you start with an excitation in one system, and then you turn on these fields and you get the swapping of the state. So that mechanism is working very well. And then in the quantum regime, you would do cooling to the ground state of both mechanical resonators. You do an excitation to a single phonon in one mode. Then you do a half swap pulse. Then you let the two mechanical systems alone. They're now in a superposition of one being excited or the other. And then after whatever long time you want to wait, you can probe again whether you're in a superposition by applying another pi/2 pulse, and then read out if you go back to exactly the same state. So those techniques are well known from magnetic resonance imaging. And here we try to develop those for optomechanics. Now, we had trouble with the mirrors to have high enough mechanical quality, because the mirror and the membrane, there's some bending at the sides, and that's always a reason for dissipation. So we tried everything to undercut the mirrors, but we got stuck to a mechanical Q of 1 million, which is still great, but it sets a significant limit. So we decided to also start investigating phononic crystal membranes. So those are not mirrors, but just a thin slice of silicon nitride, where you have a pattern of holes in there. And just like in solid state, if you have a regular pattern, you get energy bands in which you don't have states. So no mechanical states exist in these band gaps except for shear modes, but those are not excited by light coming onto such a membrane. So with those systems, then you can make a defect, just like an impurity in a crystal. Here you just change the whole pattern a little bit, and you get localized mechanical modes that cannot dissipate because they have the energy within the energy band gap. And with those systems, you can easily go to 50 million now. And that's a beautiful development. So we are now using those systems to make them also reflective. We can also put photonic crystals on top of them. And then the reflectivity can go up to about 100% in principle. And I will skip the details, but we're working hard on getting those. Here you see some of our samples. They are very good reflectors, but they're extremely angle dependent. So if the focus of the beam is too tight, you don't get, it's not optimized for all the directions of the light coming in. So we have to just make the area of the photonic crystal a bit bigger, and then the reflectivity will go up to close to 100%. Another way is to remove absorption is by using diamond membranes. And that's another development that we're doing at the Quantum Foundry at UCSB at the moment. Those would be spectacular in many ways if we can pull this off, and we're getting close of having some nice results there. So with the membranes, we were also able to do a swap experiment, but we didn't do it in the way I presented before, but we used what is called stirrup, stimulated Raman adiabatic passage. And the trick with stirrup is that you use two laser fields that are displaced in time that couple one mechanical mode to the cavity and the cavity to the other mechanical mode. And the surprising thing is, if you do that right, you have a 3-level system, but you will not occupy the optical mode. And that will prevent extra heating of your system. So we demonstrated this effect, which is this stirrup effect. We go from one state to the other by applying the right laser frequencies. And if you do it carefully, you will not populate the optical mode, and therefore the heating will be significantly reduced. Okay. So it's time to wrap up.
Dirk, I'm going to have to ask you to wrap up soon if you can, in fairness to the next speaker. It's absolutely fascinating. But please, can you try and wrap up a bit?
Okay, so we now build titanium cavities to hold these membranes. It's pretty spectacular because we can get them perfectly aligned at low temperatures, which will be published soon. We need single photon filter cavities because of this preparation of the initial stage. You come in with a laser beam, and then one photon measured on the cavity resonance tells you that you created a phonon state. So, but you must filter out this one photon, and that's the largest thing we're building right now. We also need superconducting single photon detectors, and we just were able to get 95% efficiency with less than 1 dark count per minute. So this is a huge advancement for our experiment. I will skip this, and I will just go that since Roger inspired us to start looking at things that are massive and maybe in quantum superposition stage, we started out in 2004 with cutting a mirror, put it on a cantilever. But ever since, there has been an avalanche of systems that are showing quantum effects of mechanical systems. And I have been saying for Roger to quite some time, in 2020, people will be able to really investigate your ideas. I think we are extremely close, and especially I should mention this work that was published just a month ago, where they create entanglement between mechanical excitations in membranes, part of a superconducting resonator circuit. So this is the thing I think is at the moment the closest to what Roger wants to see. They cannot keep the entanglement for long enough to prove that, to look at different decoherence mechanisms. But it's the same principle that we are doing with the membrane modes. And we're really, really very close on probing these experiments. So therefore, I give myself another few more years. But with all the efforts on levitating things, I think by 2023, really first bounds will be placed on whether the ideas of Roger are right. Well, we will not be able to prove whether they're right, but we might be able to prove that they're wrong. Yeah, so I thank Roger very much for inspiring so many people, and by pushing really the quantum limits of experiments, and in particular of larger and larger objects in quantum states. So thank you for your attention.
Well, thank you very much, Dirk, for a truly impressive and broad-ranging, shall I say, entanglement of theory, experiment, and technology, with obviously a large, great future in front of it. I think we should move on straight away, though, now to the next final talk in this session, which will be given by Philip Stamp of the University of British Columbia, and his title is The Correlated World Line Theory of Quantum Gravity. So if you could take your, unshare your screen, Dirk, and Philip, you can share yours.
Yeah, okay, thanks, Roger. Okay, so again, like everybody else, I wish Roger happy birthday for next week. I'd like to start by just, well, first of all, acknowledging the research support, both from Caltech and from UBC and from various organizations. I'd also like to give a few thank yous here to a number of people. The first is Tony Joyce, who was actually a school teacher of mine, and who was very patient with me when I told him, this was in high school or secondary school, they call it in Britain, when I told him I didn't believe quantum mechanics. And he patiently explained to me that, well, there were a lot of people that didn't believe in it, but it should be taken seriously. It was as a consequence of him that I ended up doing physics at university in the end. And I eventually met Tony Leggett, who became my PhD supervisor, and who, I guess, he had a profound understanding of quantum mechanics. He'd already done the work that got him the Nobel Prize in superfluid helium-3 and was then working on more foundational questions in quantum mechanics. And it was really him that taught me that if you're going to overthrow a theory, then you have to really understand it from the inside. Then much more recently, there was a very interesting meeting I had with Joe Polchinski. Dirk Baumeister, I was giving a colloquium in Santa Barbara about 10 years ago on decoherence, funnily enough. And he told me about Roger Penrose's ideas, which I'd never heard of. And I'll come back to that. So I told him how I think that the problem of dealing with of reconciling quantum mechanics and gravity should be done. At which point he called in Joe Polchinski, and I had a long discussion and subsequent correspondence and meetings with Joe about this, who strongly pushed me to actually publish this work. So without Joe, none of what I'm going to tell you about would actually probably have been published. He tragically died some years after that. Dirk also organized a meeting in Leiden where he, and he invited Roger to it as well, and he asked us both the night before our talks to change our subject and to talk about the problems of quantum mechanics and gravity, at which point Roger and I discovered that we agreed that the problem was interesting, but we completely disagreed on the answer. At which point Roger invited me to spend a sabbatical in Oxford, and I did, in fact, a couple of years later do so, by which time I'd followed Joe's urging to start publishing. So all of these people, Roger in particular, have been very helpful to me in keeping me focused on what I think is actually the most important problem in physics. So let me just say what that problem is. You've already heard it from many people, but let me just emphasize that we have the two most successful intellectual accomplishments in human history here, and they're incompatible. Neither of them has ever been found to be wrong, and yet they're incompatible. This is an extraordinary situation. Let me tell you before I get going here, the way I've designed this talk. I realized that there's going to be people in the audience who are specialists, who want to see details, and that there are other people in the audience who are not specialists at all, but are interested. And so I've designed the talk so that both sorts of people can get something from the talk. So you'll see lots of details for the specialists. And for those of you who are not interested in equations, I've got lots of pictures as well. And I will be focusing a lot on those pictures. So let's get going. So the view of the world, the quantum mechanical view of the world, is one that all physicists have to get used to. There's a lot of disagreement over how one should think about it. I'm going to explain how Feynman talked about this. He actually discussed it in terms of an idea which actually goes all the way back to 1695 to Christian Huygens, who imagined that you could have waves traveling by a process in which they were emitted and then traveled in all possible directions. And so Feynman imagined that a particle could get from point 1 here, I hope people can see my cursor, from point 1 here at the top left, point 2 at the top left, by following all possible paths. And during the course of doing that, the particle might emit photons, for example. But in any case, the paths were independent from each other. You summed over them. And this is Feynman's famous formula, which says how one's supposed to do that. And so this is a key point. And Feynman had these various thought experiments where he imagined a particle going through a multiple slit gateway system. And you sum up all of the different paths to get what he called the amplitude to go from the beginning to the end. There's another key idea, which is that if you have two systems interacting with each other, then they can entangle so that their states are no longer separable into two. And if you can't follow all of the degrees of freedom here, then you have to make an assumption, you have to average over them, and that's where you get decoherence, which was described in some detail by Dirk in his talk. So these are two key points coming from standard quantum mechanics. Now, people have pushed quantum mechanics a long way since its discovery, and indeed even before, because X-rays were discovered now more than 120 years ago. And this picture here, it's a well-known picture. Some people call it the Royal Road to quantum gravity, or the Royal Road of particle physics. And in 1900, we had managed to see X-rays, and their energy was of order 10 kilovolts. We're now 120 years later, and the energies currently at the LHC are of order 12 gigavolts. 12,000 gigavolts. So it's a big change in energy, and a lot of things have been discovered on the way. However, as I will briefly discuss, in the standard quantum field theory view, you have to go all the way up to a much, much higher energy if you're going to see interesting effects involving both quantum mechanics and gravity. This is the standard quantum field theory view. It's the view espoused, for example, in string theory. And you see that if one follows this logarithmic scale, it'll take us roughly 400 years before we can do experiments in this range. People have, of course, talked about the universe doing experiments for us, but in any case, we've got a long way to go before we get to this energy, the so-called Planck energy. Let me just say a little bit about how big that energy is and how far away we are from this. So here are a few lengths that one can find on Wikipedia, for example, the Planck length, the Planck mass, and the Planck energy. Now, the Planck energy is the energy I was just talking about here, way up here. It's actually a huge energy. If you gave the Planck energy to 5 tons of water, then you could heat it from 0 centigrade, from freezing point, to 100 centigrade. That's 5 tons of water. And in experiments, people are asking for this amount of energy to be deposited in what's called a Planck volume, which is very, very small because it's the Planck length cubed, and the Planck length is 10 to the minus 35 meters. So in other words, we're looking for huge energy densities. And in fact, the energy density can be calculated. Here it is. It's a very large energy density. Doesn't really matter what your units are. It's times 10 to the power of 100 and something. So for example, in gigavolts per cubic meter, it's 2.6 by 10 to the 123. Now this is 10 to the power 45 times larger than the energy densities that we have now. Just colossal. So this is the experimental difficulty in the standard quantum view of things. There's also a theoretical difficulty, and I'm going to quote here Hiroshi Oguri, who's a very well-known string theorist from Caltech, which is where I spend a lot of time. He says, it is not well appreciated how hard it is to build a consistent theoretical framework to unify general relativity and quantum mechanics. Yes.
Philip, can I just stop you for a moment? I'm getting some messages on the chat. Being concerned about your presentation and whether people can see all of it. I can, but others may not be able to do that. If somebody else in the organization can help to make sure that everyone can see your presentation.
Sure. What if I try full screen?
Yes.
Let me
try. That sounds like a good idea to me.
Okay, what about now? The problem is the same. I can see it's disappearing off the bottom.
How about the box?
You can see stuff.
Box upper right?
Sorry?
Can you click on the box upper right?
Oh, yes. More?
No, it got smaller.
Yes.
But now we see the bottom.
I'm doing so. Let me click again. Oh, no, it doesn't do anything else. So is that better?
If you go back, the whole thing is smaller, but we see everything. Go back to how you just had it a minute ago.
Well, I don't think you do. You're seeing the bottom, but not the top. you see? Huh. Not sure what to do here because I can't see what everybody else is seeing. I'm going to come out of full screen because it's just way too big. Oh man, hey, hang on. How's that? How does that look? Can people see it now?
I don't see the bottom.
Oh dear.
Now I see I can't tell what's at the top though. 10 keV, is that the previous slide or this slide?
Yeah. I think if you hold with what you've got, I think that people can see it. If it, the whole, it'll scroll as pages, but you've got the whole page exhibited. So if you go from one page to the next, you'll be okay. So I think let's just go ahead on that basis, unless anybody in the organization has a better view.
I'll continue. All right.
Okay. Let's go ahead. We don't want to.
All right. So let me just recall again. Yeah. Let me again say what Uguri was saying. He basically says here that it's very, very hard to build a consistent theory which unifies general relativity and quantum mechanics. And I think anyone who's worked on the field knows that. And then he says, currently, superstring theory is the only credible theory to have achieved this unification. I am actually going to strenuously argue that that is not the case. But let me say that there is some skepticism out there about this string theory point of view. I'm just going to give you one quote. That's from Frank Wilczek. He says, string theory has failed to deliver concrete predictions, let alone successful ones, as have other less heralded high energy approaches. Okay. Now you notice that all of this assumes that the answer is to be found at extremely high energies. So that's, if you like, the standard quantum mechanical view. Let me now go to general relativity, and I'll be very short here because everybody's been talking about it. As we all know, we deal with a space-time which can be defined by a metric and by intervals and so forth. And there's a key principle, the equivalent principle, which roughly speaking says that gravity doesn't distinguish between different forms of stress energy. It's completely blind to whether you're dealing with an electron or a photon or whatever, just so long as it just simply sees the stress energy. And this is also true of itself. It sees itself as a source of stress energy, which is why it is so interesting a theory. And of course, both quantum mechanics and general relativity have had enormous success. Just very briefly, I'll talk about their problems. Let me first of all recall some of the problems of quantum mechanics. One is that we have no real understanding of how it can work at the macroscopic scale. This is sometimes called the measurement problem, or what macroscopic superpositions of states would really entail. The second is that we have a state vector, at least in many of the formulations, which is either taken to be a real physical object, in which case we get paradoxes like the Einstein-Podolsky-Rosen paradox, or is taken to represent information, but then different observers assign different kinds of information, and we'll lose all reference to the physical world. And again, if you then promote this to the macroscopic world, it's hard to know what you're talking about. It's also very peculiar because it revolves around measurements and operators and so forth, but which are treated differently. Hence the idea of the collapse of the wave function. And in fact, one gets the impression that looking at all of this, that we're dealing with an awfully medieval kind of formulation here, in which is completely anthropocentric. It all revolves around measurements and people, and often people even invoke consciousness, which is reminiscent of the Middle Ages. The upshot of this is that many people say that we don't really understand it. Dirk Bouwmeester mentioned Bohr. Feynman said the same. I think I can safely say that nobody understands quantum mechanics. He said this in his messenger lectures in '65. Now, general relativity doesn't have quite such obvious problems, but there is the problem of singularities, which many people feel is also something that has to be dealt with. But most important of all is the incompatibility of the two. Now, Roger has talked a lot about this, so I won't spend a lot of time on it. But imagine we're dealing with a situation where we have a two-slit experiment, and so an object can follow one of two different paths, and you can attempt to look and see which path it's followed if you want with a detector. The problem here, first of all, that we have two different space-time metrics defined by the two different paths for the matter. And this, as was discussed by many people, there's a nice discussion by Bob Wald in his book, leads to a problem with causality because the fields that exist on space-time are defined, their causal relations depend on the commutators. And if we then apply this to the gravitational metric itself, we find that that causal influences, whether or not they can propagate between 2 points in space-time, depend on the metric. But the metric, of course, can be changed, and apart from anything else, by quantum fluctuations, which will then change the causal relations between matter fields, which then basically gives you a nonsensical theory. But you notice, and this is the key point I want to make here, all of these problems, and people have been talking about them for a long time, are not problems at the Planck energy. They're problems at low energy. They're problems in our own world of tables and chairs. So this suggests that we've been looking in completely the wrong place, or at least a lot of people have when they try and unify quantum mechanics and relativity. Now, a lot of people have talked about this. Feynman was one of the first. Let me pass through this quote since we have a time problem. And come to this. For various reasons, which I won't go into, he said, I would like to suggest that it is possible that quantum mechanics fails at large distances and for large objects. If this failure of quantum mechanics is connected with gravity, we might expect this to happen around the Planck mass, which is about 10 to the minus 5 grams, corresponding to 10 to the 18 particles. Now, since then, many people have talked about this. Let me first of all emphasize Roger's contribution, which you've already heard about from Dick Baumeister, so I'm not going to go through it again. But let me just emphasize what Roger said here. None of the considerations of the present paper give any clear indication of the mathematical nature of the theory that would be required to incorporate a plausible gravitationally induced spontaneous state vector reduction. That's a rather long sentence, but basically what he's saying is that he's got thought experiments, but not a theory. However, as you heard from Dirk, they did propose experiments to check out these ideas. Now, as I said to you that I had actually no knowledge of Roger's contributions until I talked to Dick Baumeister, but I had looked very extensively at work by Kibble, which was considerably beforehand. And this is very interesting work. What Kibble tried to do was essentially turn quantum mechanics into a nonlinear theory by incorporating gravity into it, but in a fully quantized way. What he noticed was that if he tried to do this whilst keeping the usual quantum mechanical structure of operators, measurements, and Hilbert space, it wouldn't work. I'll leave you to look at his papers on this. Similar conclusions were arrived at by Steven Weidenberg and Joe Polchinski, which is in fact why Joe was, as a string theorist, interested in low energy arguments of the kind I'm going to give you. So this is, if you like, some of the interesting history, but there's another kind of interesting history, which I think perhaps people are less aware of. We've heard from a number of people here about tests to see how big we can make quantum states. Actually, a lot of work has been done on this. There's been work on superpositions of spins, superpositions of masses, and so forth, and you've heard about this. And also superpositions involving superconductors. These were initiated by theory of Leggett, and there's a lot of work been done. But here's the bottom line. The numbers are small. So for spin systems, they've never seen superpositions of more than 10 to the 3 spins. As you've just heard in the previous talks for mass superpositions, well, we were told 25,000 AMU in the talk of, in one of the talks we've heard. And in fact, a very nice analysis by Brigitte Worley has shown that in the squid experiments, the entanglement involved is actually no more than a number of about 6,000. So in other words, quantum mechanics is very, very far from being demonstrated at the macroscopic scale. And this is a key point. It's extrapolated all the way to the universe, but we have no reason to believe it above these very small scales. Now, there are recent developments, and again, they've been talked about in previous papers, so I'll just briefly give, for those of people who want to look at this talk later, they can get the references from here. And actually, almost all of these have been mentioned already. So what I'm going to talk about now is a theory which is in fact a counterexample to what Uguri said, in the sense that you can devise a consistent theory which incorporates general relativity and quantum field theory. And this is called the correlated world line theory. So let me first of all, in a very hand-waving way, tell you what the fundamental idea is. I already mentioned that a key feature of general relativity is that gravity doesn't distinguish between different fields. But one can extend this point if you start talking about quantum mechanics using paths. You can ask the following question. Supposing I try and distinguish two possible scenarios. One is where I have one particle executing multiple paths. The other is where I have two particles, which are indistinguishable, executing the same path. Is there any particular reason why gravity should be able to distinguish between these? And the answer is no. But if that is using the picture at left, which is the conventional quantum mechanics, but the picture at right, in which because gravity can't distinguish between interactions between a pair of particles and interactions between paths for single particles, we have to include these. And our guide is in fact the equivalence principle. So there's a lot of papers here, which one can look at. And for those who are interested in the technical side of this, there was a meeting recently organized for the 100th anniversary of Sakharov, in which I gave a more technical talk on all of this. This is what you have to do in a Russian meeting, be technical. So I'm going to not be technical, but I will just in passing note that the kind of framework you need is not one of, for example, quantum field theory in curved space-time. That's simply not good enough. You have to fully quantize gravity as well. Okay? We're going to see that when we do this, following the idea that paths for the same object can interact with each other, that we end up with a very interesting theory in which, in fact, classical gravity is recovered. Okay, so this is all for the people who are familiar with technical details. But one of the most important things that we did, and this is particularly my work by myself and Andrei Barvinsky from Moscow and with Jordan Wilson-Giraud in Vancouver. Jordan is now going to Caltech, is investigate consistency. We wanted to make sure that all possible consistency checks for this theory were obeyed. So what that meant was looking at to see whether the expansions in powers of the coupling constant, that is the Newton's constant, or powers of H, the Planck's constant, were obeyed, whether we got a consistent classical limit, and whether all Ward identities were obeyed, including diffeomorphism and variance identities. And this worked for all of the things. So we were satisfied that we had a consistent theory. And then what you have to do is in conventional quantum gravity, you could imagine a particle going between two space-time surfaces here, hypersurfaces, and emitting a graviton and reabsorbing it. But in the CWL theory, we see that two paths or three paths for the same particle are exchanging gravitons. For the same particle, that's the key point. So I'm not going to go through any of the formalism here. I'm just going to tell you the results. The first result is that for this field theory, one can write down a generating functional, and it actually can be found exactly. We first of all found it using an Eikenlohe expansion, then we realized that the result was exact. And the result actually tells you that no matter what the mass of the object is, the metric field behaves classically. This is utterly different from theories in which the metric field is utterly different from conventional quantum gravity, because in conventional quantum gravity, the metric field will be different for different quantum states. okay? However, this metric field is not reacting to a classical path for matter. It's reacting to the sum of all of the quantum paths. And these quantum paths are interacting with each other through the distorted metric sourced by these quantum paths. I'm going to show you a little bit later how this works. But we also find that for the matter propagator, we can get an exact result. And the result, I'm not going to discuss the formalism here, is that the particle propagates in the Einstein field produced by all of the paths, but it still shows superpositions. However, those superpositions only work in the conventional way if the masses are small. So let me just say this all again. We find an exact result, which is the matter propagator still propagates along different paths, but these paths are interacting with each other. If the mass of the object is large, those interactions are strong, and that will cause something which I'm going to call path bunching, and I'll show you about that later. However, the metric field still obeys the classical Einstein equation, but in the field of all of these different paths. Okay, now I think that it's very important that that we talk about the predictions of the theory as opposed to just a mathematical structure. And it's also important that we discuss the kinds of examples that will be important in real experiments. So that's what I'm going to do actually for the rest of this talk. I'm going to talk about the quantitative predictions of the theory. And I should emphasize that there are no adjustable parameters in these predictions. We're not introducing extra parameters as in, for example, the collapse theories. And again, I should emphasize that as far as we can tell, this theory is consistent internally in all respects. Okay, so one goes to perturbation theory. I'm not going to talk about the formal stuff here. This is for people that might be interested, but you can actually and it's very interesting because for small masses, you find that things like radiation reaction and so forth are quite different from what you would expect from standard quantum gravity. But for large masses, you get the strong interactions, if you like, between the paths here, cause the paths to collapse onto a classical path, ultimately. Ultimately, they will collapse. The key question we will want to answer is, how does this collapse happen? We'll see that there's nothing like the collapse that's talked about in measurement theory in standard quantum mechanics. So let's work up to this slowly. I'm going to start off by considering a really simple problem, which is a single point particle. Now, of course, in reality, we don't have single point particles unless we're dealing with elementary particles. But let's start off by just asking how a single point particle behaves in this theory. Again, this is the formal calculation, but I'm now going to ask what happens if the particle is moving very slowly. So let's imagine we have, say, an electron moving in intergalactic space, so it's not interacting with very much. It is, of course, interacting with the surrounding photon bath, but we'll ignore that for the moment. And assume that it's moving slowly. In that case, to lowest order in the gravitational coupling, we have a Newtonian interaction between a pair of paths for the particle. Remember, of course, that in ordinary quantum mechanics, there would be no interaction between the paths. That's the whole point of quantum mechanics. That's what's called the superposition principle. But here, the superposition principle is broken down because we have a gravitational coupling between different paths for the same particle. And that's shown in this picture. Here I'm showing two paths for the same particle. And remember, this is a free particle moving in intergalactic space. And these paths are attracting each other, which of course means that they'll actually oscillate around each other. In other words, they won't move independently of each other. They'll actually oscillate around each other. Now one can actually look at the characteristic scales of this attractive potential for different masses. There's a characteristic length scale, which is, if you like, the radius of the potential. This is the analog of the Bohr radius for Coulomb attraction. That's what we call LG sub m. Notice it goes like the 1 over the cube of the mass, m of the particle, and this is m sub p is the Planck mass, L sub p is the Planck length. Then there's an energy, which is essentially the binding energy of these two paths. It's the analog of the ionization energy for a hydrogen atom. And I won't use this. That's the Schwarzschild radius for the particle. So let's have a look at how this works out for different point particle masses. I hope people can see all of this slide. So on the top, I'm showing the results in pictures, and on the bottom, I'm showing them in numbers. Let me do the picture first. The left-hand picture shows how the size, if you like, of this bound pair of paths varies with the mass of the particle. So down here, at 10 to the minus 30 kilograms, I've got an electron. A bit further up, I've got a hydrogen atom. Up here, I've got 10 to the 7 hydrogen atoms, and of course, there's no particle of that mass that we know of, and so on. And this is the length scale. This is, if you like, the size of the pair of bound paths. And you notice for an electron, it's very big. Actually, if I calculate it, it's 4 million Hubble radii. In other words, it's far larger than the universe. But as I increase the mass of the particle, that radius gets much, much smaller. The right-hand graph here is the binding energy of the paths. It's how much energy you need to actually break the paths apart and essentially make the thing behave like a free particle. And again, for the electron, this is a very, very low energy. In fact, we see that it's 10 to the minus 84 electron volts, which probably means nothing to non-physicists. But what it means is that if you allow these paths to oscillate back and forth, they would do it at a frequency of 10 to the minus 70 hertz. That means a time scale of 10 to the power 70 seconds, which is so much longer than the age of the universe, the number is just meaningless. In other words, the effect on the electron is absolutely negligible. But now let's increase the mass of the object. If I go to a vaccinia virus, now this is not a point particle, let me emphasize. It's got a radius of actually 3,000 angstroms, which means it's about the size of the wavelength of ultraviolet light. And it's got a much larger mass than an electron, of course. But it's interesting to see now what's happened to these energy scales. Instead of 10 to the minus 70 hertz, we've gone to 10 to the minus 5 hertz. And in fact, this is a time scale of order 10 minutes here. In other words, they oscillate let me go back to this picture before. Two paths, because of this attraction, will now oscillate with respect to each other, essentially orbit around each other on a time scale of 10 minutes. And the radius there is now much, much smaller. You see that it's actually about the same size as the virus. Now, of course, you realize that this means that the calculation is no longer reliable. We have to take account of the finite size of the virus. In fact, there's a whole bunch of things wrong with these little estimates. And let me just tell you what they are. I've called it a toy model. The first thing is I'm only kept looking at pairs of paths. In fact, we have to deal with interactions between triplets of paths, quadruplets of paths, and so on. And it's a perturbative calculation. So if the mass gets large, we have to go beyond this lowest order result. There's another problem, which is that we're dealing with an extended body. And as you've just seen, the interaction between two paths for a single body is not going to be the same as the interaction between two paths for a particle. But there's another problem as well, which is that the particle moving along these paths will actually couple to its surroundings, which turns out to be a very important process. Let me just very briefly know why it's an important process. If I only incorporate gravitational interactions here, then these paths will oscillate back and forth with respect to each other because of the gravitational interaction indefinitely, in the same way that two planets, in the same way that two isolated stars will orbit around each other indefinitely if you ignore gravitational radiation. So the fact is that we need to know what the coupling to the surroundings is, because that's going to cause these oscillations to decay, and eventually the paths will amalgamate into the classical path for the system. So let me deal with this first problem here. The problem, which is that the large bodies are actually extended in space. And so we now have to find out what is the interaction between the paths when we take that account of that. The results turned out to be very interesting. So the calculation I won't bother to explain, but we now find that there's a new effective interaction between pairs of paths for the center of mass coordinate, which is quite different from the 1/r potential that I showed you before. And for an amorphous system, so we could imagine that our solid body is just glass, for example, we see the following shape. We see what looks like, at least for down here, looks like a harmonic well with a spike in the middle. Now that spike is actually coming from the nuclei. If you try and move one object with respect to the other over a small displacement, you've got very strong gravitational interactions between the nuclei. However, the width of this is not, I repeat, not the same as the diameter of the nucleus. In fact, it's much larger because the nuclei exhibit 0-point motion at 0 temperature, and at finite temperature, there's also thermal oscillations. So in fact, the width of this spike here is actually, it's parameterized by this parameter sigma, which is actually about 1% of the distance between atoms in a typical solid. So in other words, 10 to the power 3 larger than the radius of the proton. So we now see that the paths that we have will oscillate with respect to each other in two different ways. If they're already at low energy and sitting at the bottom of this potential well, they'll oscillate back and forth in this spike potential. But if they're not at low energy, then they'll oscillate in this much bigger potential with perturbations from the spike. Now, the interesting thing is that the frequency of these oscillations does not depend on the size of the system once you get to a big enough system. That's a really extraordinary result. The time scales can be calculated very precisely if you know the structure of the system. For example, if it's amorphous, if it's crystalline, and so on and so on. So here are the answers for amorphous silicon. The oscillations in this spike potential have a time scale of 16 seconds. The oscillations in the big smooth potential have a period of 21.2 minutes. That's for amorphous silicon dioxide. So that's very interesting. It's telling you that in reality, if you look at a large mass, it will not, and you can make it, you can get rid of environmental decoherence of the kind that Dirk was talking about, then in fact, you will actually see the object not spread out in the way that one expects, whether it be in empty space or in a harmonic well or whatever. It will actually show these oscillations that I'm talking about of the relative coordinate. I won't have time to talk about how one can see that in experiments. This is something that people are working very hard on, certainly at Caltech and part of the LIGO project. But what I will tell you is that there is another key prediction of the theory. So I have not yet mentioned the fact that this system couples to its environment. And the coupling to the environment is something that's been very well understood with increasing understanding over the years. It was first pointed out by Feynman and Vernon that one could build a general model at low energies for the coupling of a system to extended environmental modes. These are things like phonons or photons and so on. Electron hole pairs if the system is metallic. And the theory of this was worked out in great detail to the point where it was highly predictive, essentially by Leggett and collaborators. And by the way, this is long before Zurich. However, there are we've called spin bath modes, and these are localized. So they could be defects, nuclear spins, paramagnetic spins, even modes on dislocations and so forth. And all of these exist in solids, and you have to take account of them. And in fact, in the LIGO experiment, they are the main source of dissipation, particularly the surface of the mirror. So these can also be dealt with, and these are the papers for the formal theory. Now, supposing I ask the following question, which is, how long did it take these oscillations between different paths to decay because of this coupling to the background. And so for the system to finally show what people call in convention, never mentioned wave functions here, and I'll say why in a minute. Well, the answer is that if you design the experiment well, it can take an awfully long time. So for example, for LIGO mirror, you can have a Q factor of 10 to the 10. And the time scale for this path bunching, in other words, the final decay to the classical state, then is of order 10 to the 10 times 16 seconds, and that's 5,000 years. In other words, how you set the whole system up depends very much, how the path bunching occurs depends on how you set the system up. Of course, you can reduce this time scale enormously, but it's clear that this is not really the right way of doing the experiment. And in fact, there are all sorts of interesting designs coming out of Caltech for how these experiments should be done to test all of what I've just told you, which I don't have time to talk about. So let me now, and I think I'm okay on time here. Let me just conclude. There are certain assumptions involved in a theory of this kind. One is that we're not dealing with many worlds. We're not dealing with a quantum classical divide, and we're not dealing with wave function collapse. In fact, we're not dealing with wave functions at all for the reasons that I gave early on, that as Kibble showed, if you start off with a theory that looks too much like quantum mechanics, you're kind of doomed to failure when you try and incorporate gravity. We're in fact dealing with one reality, and that turns out to be fundamental in the formulation of the theory. You can formulate a theory which is consistent. So this is a counterexample to what was said by Uguri, because remember, and we've incorporated general relativity all the way along the line. And we've ended up with a fully quantized theory, but which becomes classical in a certain way as you increase the mass of the system. Okay? You can think of it as a kind of a nonlinear theory of the kind that Kibble was looking for, in which gravity generates the nonlinearity and destroys the superposition principle, but it's fully quantized. The primitive objects in this theory are paths or histories. It does involve a 4D space-time. I have a lovely quote from Roger about why one shouldn't abandon 4D space-time, but I couldn't find it in time for this talk. We see that superpositions are suppressed with time in a complex way. We also notice that there's nothing special about measurements here. Everything has got to do with gravity and mass. And whether or not you have conscious beings around is utterly irrelevant to this theory. So finally, let me just say something about my collaborators here. Andrei Barvinsky was extraordinarily helpful because he came from the Russian School of Quantum Gravity that I found most congenial when I was trying to do this. Dan Carney was a postdoc who's now got a position at Berkeley. Yanbei Chen should be well known to many of you. He's took over Kip Thorne's position at Caltech. And then my two students, Colby Delisle and Jordan Giro Wilson. Jordan's actually going to Caltech in a month on a Burke Fellowship. Secondly, I should thank the so-called G5 group. This is a group of us that regularly discuss and try and collaborate together. And that's Marcus Aspelmayer, Yanbei Chen, myself, Bill Unruh, and Birgitta. And we're all thinking about this theory. And then finally, I'd like to thank various people who have contributed over the years, notably Roger, because he was the one that I never had fully appreciated the subtleties of classical relativity until I spent a few months at Oxford with him back in 2013. Alexei Kitaev has come up with all sorts of ways of applying this theory to other problems. And well, let's see. I guess I've run out of time, Roger. Is that correct?
You're allowed a few parting thoughts. But yes, go ahead.
Okay, well, then
completely fascinating. So keep on going for a few sentences.
Well, okay. I mean, so fascinating ideas about quantum information have emerged from Birgitta in the context of this theory. Alex, you've got all sorts of ideas about how to apply this to cosmology. Well, Kip and I have talked about closed time curves in the context of this theory, but we haven't come up with anything yet. And he's too busy writing books right now. Let's see. Oh, Alvaro Gomez was a postdoc of mine who had some really interesting ideas as well. I think I have stopped here. I haven't got pictures of them all, so why don't we just stop there?
Okay. Well, look, thank you very much, Philip, again for yet another excellent and very provocative and instructive talk. And personally, the notion that LIGO might experiment fussing around with the LIGO mirrors and trying to improve, I think might actually lead you to quantum gravity. I find a lovely thought.
Stay tuned, because we think we're quite close. Bill and Yan Bei have played an essential role there.
Oh, okay, so that's great. So look, we've got to the end of our four talks, which have been, for me, very enlightening. I'd like to open this up for general discussion, and as was mentioned at the start, the medium really is the Q&A, and there are questions that are coming through. I'm getting there's a bit of a lag for me, I think, but I'm going to firstly ask the four speakers to unmute and bring up their videos, and I think they've done that. And Roger too, please, and Roger Penrose as well. So I've got a question here. In fact, I've got two, I think, from Michael Wiest. Regarding tests of quantum mechanics for macroscopic objects to date, don't neutron stars require a quantum description and thus represent empirical evidence that quantum mechanics applies to large objects? So who wants to take that on?
I'll have a go. I think this point was answered very convincingly a long time ago by Tony Leggett, who pointed out that he called it disconnectivity, but we now think of it more in terms of entanglement. The actual entanglement is very, very small there. There are no macroscopic superpositions involved at all. Let me explain it in a way that was first given by Phil Anderson. You can map a Bose condensate onto a set of spins. If those spins all happen to be pointing in the same direction, then the mapping to a Bose condensate is exact. But nobody would say that a system with all the spins pointing in the same direction is in a macroscopic quantum state. And the same arguments apply to a neutron star.
Yes, do anyone of the other three presenters want to add to that?
Yes, yeah, if I can chip in here. So I would agree, it's quantum mechanical, the neutron star arguably, but it's the wrong state, right? I mean, and I would even go so far to say that also entangled states of two masses are not the right quantum state to probe these ideas of, wave function collapse or, the effect of gravity on superposition. What you really need is a single mass in a superposition, and then a set of parameters count, so that the distance or the size of the superposition, the mass which is involved, and also the time for how long the state exists. I think that is the right set of parameters. And if you put this in, which has been done in literature already, so also the experiments with Philip mentioned in superconducting circuits, so inspired by Tony's work. So they can be compared to other matter wave interferometry experiments, and you see that they're actually quite small because the superposition state is actually not of a large spatial size. Yeah.
Okay, well, thank you very much for those two answers. I'm actually going to continue with Michael Wiest, and because it just come up, and it was a rather different question, and I'm going to read it here. Under what conditions does pumping energy through a quantum system combat the effects of environmental decoherence, as in the Froelich model? Is this a viable approach for achieving coherent quantum states at room temperature or above? Who wants to take that on?
I can say something if you want.
Actually, it's a little bit related, but I now appreciate it, but go ahead.
Well, the fact is that the Froelich state is not a Bose condensed state. It's simply a pumped state. So there was a discussion a long time ago about how Perhaps you could create macroscopic quantum states in cells by creating Froelich state for cell walls. But the fact is that it's not a macroscopic condensate. It's not a Bose condensed system with, it's not even not really even a Bose condensed system, and it's certainly not a macroscopic quantum state.
Anybody else want to add to that?
So I can also you know, say something about this. So you know, with these things, if you pump energy through something, and you look at this again from the point of view of the coherence mechanisms, as was explained by Dirk for an example of a two-level system. Of course, if you have a macroscopic quantum state, which may be, you know, one of the systems I explained, then there are many of those decoherence mechanisms, and I fully agree that one has to study all of them. And then it always boils down to comparing again parameters of this decoherence process. So that is again, you know, what is the length scale which can be probed by the specific process, yeah, and what is the rate of the probe. So how many measurements you take per time, and by that you can actually, you know, quantify and exclude and study all these different processes, and you also learn, you know, which is really, you know, a killer decoherence and which is not. Yeah.
I've got here a question that seems a little bit related from Zach Martinez. And he writes, with regards to experimental upper bound for mass in achieving quantum superposition, molecules greater than 10,000 AMUs have been successfully delocalized as a single particle, upwards of 800 total atoms. Does anybody want to comment on that?
Well, I could say something about that. Marcus Arndt, where Hendrik actually worked with him, so I'm sure he can add to that too, has, you know, the record on making these macroscopic superpositions with very, very big molecules. However, the masses are still many orders of magnitude below where you could expect to see gravitational induced collapse.
Does anybody else want to add to that?
I showed in one of my last slides this work from the Teufel group from May this year, and that they talk about a 70 picogram membrane, but of course it's not just the mass that is important, it's also how much is it displaced, and they don't give any details on that, but it's definitely an entangled state of two membranes, and each about 70 picograms, which is, I think that's the record for entangled states with massive objects. But it's—
And the mass distribution also matters a lot. So
sure.
It's very different, the collapse time when you get a sphere than when you get like a two-dimensional or one-dimensional geometry.
Yes.
And again, if I can make my point here, I think, you know, if you have two masses which are entangled, it's a different state, and I think it's less sensitive to, you know, the question we are after. Instead, if you have a single mass which is in a superposition of two locations, so it's a different thing, and you can compare it. So there has been an attempt to, you know, formalize this in what is called macroscopicity, which is a measure which compares these different systems. And I also know that there are different of those measures which are, you know, not in agreement, but I think it's a different, you know, quantum state. An entangled state is a different quantum state than a single particle superposition, and that is, you know, we have to be careful with this when we compare it. That's maybe my comment.
For the membranes, if they are entangled, you still talk about each individual one having two different locations.
Yes, but then
two terms. So
yes, I agree.
Calculation would come in.
Yes, I agree. Then you have to look basically for each membrane. What is the mass? It's huge. But then if you look at the superposition size, so what is typically done is you take the extent of the 0-point motion to estimate basically the size of the superposition. And that is tiny. That is, I don't know, 10 femtometers, I don't know, it's really small, maybe picometer, but still. And then the time, so for how long can you generate the superposition and you can keep it? If you put these numbers in, you find that the actual bounds which you set on, you know, these models or these ideas are weaker than the bounds which come from Marcus Arndt's experiment, because he has a single mass and he has, 100 nanometer separation. Yeah? So that's the size of the superposition state. And that is what is basically winning, yeah, in this respect.
I actually have a question about that, because the calculations that Roger proposed for the gravitational self-energy, like Henrik said, apply for one single system. But if you now have two systems, then you would have sort of the self-gravitational energy of each system with itself, plus the normal gravitational interaction between the two. So I don't think it has actually been theoretically calculated what is the reduction time of such a state. And it's actually highly non-trivial how to calculate that.
Yes, yeah, I agree. And it depends actually on the actual setting, right? It could be that these two effects, so you have basically the self-gravity here, the self-gravity here, and then you also have the gravity between the two. It could be that it is not helpful, right? And it depends on the distance, of course, and all these things. So I agree.
I've never seen a calculation. Yeah. I have never seen a theoretical calculation of that yet.
Yeah.
But that's going to be orders of magnitude smaller than the part of the individual components moving.
Yes, yeah, that's my expectation as well. Yeah.
So that can be ignored.
Yeah.
But the whole point of all these experiments is that you can get things in quantum states and entangled states by going to higher and higher frequencies, by stiffer and stiffer systems, and there's a lot of activity because you can use it for quantum memories and it plays into the game of quantum information science. But you're not aiming for large displacements. So we make life very difficult for ourselves by going to low frequency oscillators.
Exactly, I know. Yes.
Large displacements. So that's not too many people appreciate that it's easy to get something of 20 gigahertz in a quantum superposition, but something at 10 kilohertz or even lower. That's what you need to get also large displacement.
Exactly, yeah. So for high frequencies, you just put it in a fridge and you're in a ground state.
That's right.
So everyone else has contributed to this discussion. Roger Penrose, do you have any thoughts on what you've just heard?
Well, I was going to query something about Philip's talk, if I may.
Please do.
In fact, I have great trouble with the path integrals because what space are they in? You talk as though it's space-time, but then how is GR described as a path? There's something I deeply don't understand about it.
Good. Okay, thanks. So, so you're quite right. One has to define the space in which the paths are defined. One also has to define a proper measure for the integration over the paths. So you're probably familiar with the earliest attempts to do this for gravitational path integrals coming from DeWitt a long time ago, and he defined superspace, and a measure was then defined there. But of course, this doesn't really mean anything unless you constrain in some way the different possible configurations of space-time. If you allow anything whatsoever, then you get, well, pretty much nonsense, because you can, first of all, we have no idea what the different possible configurations of space-time are. And second, we have no idea how to calculate measures over, for example, different topological configurations. Yeah. So the argument, sorry.
I say I appreciate those difficulties, but I wasn't understanding what you were doing. I mean,
so one thing I didn't properly discuss in the talk is that I do not want to use this theory except at low energies. I don't believe that one can extrapolate this kind of thing to very high energies, and certainly nowhere near the Planck scale. So in other words, we don't have any changes of topology, and we don't well, I beg your pardon, we can have changes of topology if, for example, black holes appear and so forth. But otherwise, we're dealing with a low energy effective theory.
But how do you describe a black hole in your theory? I'm not quite sure.
Well, all I can say is that in the theory, the metric field itself is proven to obey the classical equations. But how, so in other words, if we define the theory in this way, assuming that it's a low energy theory, then we get back the classical relativistic equations for the metric field. And of course, black holes will then appear. But then you can then argue that there's a contradiction in the sense that there will be regions of very high space-time curvature there. And I can't answer that problem right now. But what I can say is that you can define a measure for path integration of the metric field under these circumstances.
But I still don't have an intuitive picture of what you're doing. I mean, you're talking as though the paths are in something like a space-time. I mean, a lot of when you were
the path, you mean for the path for the matter fields or the path for the
particles
field?
If you're talking about path integrals, what is the path that you're talking about? What space is the path in?
Yes, are you talking about the matter fields or the metric fields?
Well, any. I mean, presumably, if you're doing a comprehensive theory, you include both particles and well, are they gravitons when you're talking about particles, or are you considering?
No, I'm distinguishing between matter fields and the metric field. Okay, so if you're asking how one defines the paths for the matter field, it's a different question from how you define them for the metric field. So I mean, I don't think that let me say that we've had this discussion before, Roger, and there are a number of objections that you have. The first one is, for the path integrals for the matter field, your question is, well, what do the initial and final points mean in a diffeomorphism invariant theory? So that's one objection.
What any of the points mean? I mean, what is a point in this case?
I understand, yes. Yeah. So when you do this in the way that I described, so this is the technical discussion. That's why I showed the technical slides, which contain, you know, the various Faddeev-Popov determinants and so forth, which are designed to deal at low energies with the kind of problem that you're talking about. So they deal with the diffeomorphism invariance. So as in any gauge theory, you pick one gauge, you do the in the old style way of doing it, you pick one gauge, you do the calculation in that gauge, and then you integrate over all gauges and divide out what's called the volume factor, okay, to get a result which is gauge invariant. There are, of course, more modern ways of doing this, but roughly speaking, they amount to the same thing. So, and the kind of problem you're talking about there does not just happen in gravity. I mean, it happens with any gauge theory.
Yeah, I can understand that difficulty, but
well, the point is that, in my opinion, this difficulty was solved a long time ago.
I'm going to step in here. This is an absolutely fascinating discussion, and please continue it. But as we're running out of time, and there are many lovely questions out there, I'm going to bring up one here for Hendrik Ulbrich from Ranjit Nair. How do you respond to the late, you did actually cover this a bit, but I think you asked you to say a bit more. How do you respond to the late Steven Weinberg's observation on collapse models such as CSL that they entail a violation of faster than light signaling?
Yeah, that's a very good question. Actually, the trick here is that that's why you have the random field, right? So if you would have not the effect of the random field, so like for instance in the Schrödinger-Newton equation, you would have a violation of faster signaling than light. If you include this random field, the noise, then you can circumvent this. So that is the one of the cool tricks of these collapse models, which they do. Yeah.
Can I make some comments here? Sorry.
Yeah, please.
One point I should make is that CSL models, I have some notes which I'd sent around. They got sort of killed off by the Nobel Prize, so I have to go back to them. But one of the last things I was discussing in these notes was that you have difficulty with all CSL models. That the trouble is that the collapse time seems to depend on the amplitudes. And this gives you a way of signaling faster than light in an EPR situation. So I think it really has to be answered. I think that if you're going to take the CSL model seriously, you have to address this question. It's not been made very public because it was only in the notes that I sent.
Yeah. No, I take your point, Roger, and that will be done. So I'm not the right person to do it. I'm an experimentalist. but I know that Angelo is working on it, and they're doing the calculations, and they will publish this. Yeah. But I mean, my answer was the short, intuitive one.
Can I ask a question here, which is related to what Roger is saying?
Please do.
And this is something that Roger and I have certainly discussed last summer when he was writing his notes. And I've also discussed it with Basti and Dioschi. I'm going to put the question in a very provocative way so that the experimentalist can't say, oh, I'm only an experimentalist. This is a theory problem. So here's my question. You have a theory here, the CSL theory, which is...
It's a model, it's not a theory. It doesn't make a claim to be a theory.
Okay, I think you're already answering part of my question. So we have a model here, which essentially is derived for one purpose only, to solve a problem which is sometimes called the measurement problem. Yeah. It's not covariant. It really doesn't fit with the rest of physics. It doesn't conserve energy because we have this noise field coming from who knows where. It leads to bizarre things like superluminal propagation and so forth. Why would anyone take it seriously? It reminds me of the epicycle theory, in which you continually add epicycles with no fundamental justification, trying to fix one problem without ignoring everything else. So I don't understand why experimentalists are taking it seriously.
I mean, okay, so I take the provocation. I think it's not entirely fair to do it in this way, but I'm happy to answer. So I think that you know, it is a starting point, and the starting point is really, you know, with quantum mechanics. So you want to solve the measurement problem, and you want to produce something which is consistent with the Born rule, so which is reproducing the statistical outcomes of measurements. So that is what these models can do. They're not allowing for faster than light signaling. So, you know, that's a point which will be addressed, and, you know, which is being worked on. There's a version of these models which actually fix the energy conservation violation thing. So they're so-called dissipative CSL models. I fully take that, you know, it is all a bit reverse engineered. But, you know, what I like as an experimentalist, and that was your question, is that it is a clear dynamical model, yeah, which makes a prediction, yeah, for the outcome of a measurement. And that's something which I can test. Yeah? And I do the experiment and I test it against the prediction from quantum mechanics. Yeah. So that's it. That's a simple answer. Yeah.
It's well worth studying because it is a specific model to look at. But I think it has difficulties. And one of the difficulties is the spontaneous heating. Yeah. And I think you need a model which doesn't have spontaneous heating. And the kind of thing I actually mentioned in my talk yesterday, although only very briefly, was there is some indication of the kind of model that wouldn't have spontaneous heating. And you have to look at such models. And I think there are experiments that one could do. They need to be worked out a little bit more to test this class of theories.
Yeah. And then, I mean, I have to say, then there's another argument, which is more like the luxury of being an experimentalist, which is that, you know, I don't have, you know, to put my full heart into this model. It is just a model which I can test. And then if I do the test and it doesn't show up, I go to the next. Why not, right? It is just a model. I don't have to, you know, put all my faith into the model, yeah? Which I understand it's more difficult for, you know, to do, you know, theoretical work. And I feel a little bit guilty to take a shortcut here. But, you know, it's something which I can test. Yeah. So I think it's at least in part a good answer. Yeah.
No, I was just going to add that the really important thing here right now, and I think the experimentalists are very close to that, is reaching those scales. Because once they reach those scales, like Hendrik said, they can compare different models. And then, you know, like I, as a theoretician, I'm just like waiting closely to see any experimental results. So then I can feed back that into a theory. And I think that's what's been really lacking so far.
Okay, thanks, Yvette. We're going to have to wrap up very soon, I think. But the name I recognize, but one never knows, on the web, David Brin. And he starts with two propositions. One is, in quantum mechanics, time is the stable invariant. And then in gravity, the invariant is the speed of light. And then the question is it possible that there is an intermediate regime where this transitions? Does anybody want to take on those propositions and then the question? About invariance.
Well, you need, yes. Well, it's quite right. I mean, well, Yvette was talking about, I mean, you have models of quantum mechanics where the time is definitely a thing, and it's contradictory. It contradicts with the idea in space in general relativity, where you don't have a time. You've got the light cones instead. So instead of having these flat surfaces, if you like, which are successive times, you've got these light cones. And ultimately, we've got to deal with a theory where you've got the light cones instead of the flat times. But whether they are definitely determined, or that can bring quantum mechanics in, you're certainly going to have superpositions. If you have macroscopic superpositions, you're going to have not well-defined light cones. They're going to be in superpositions, or you're not even going to have well-defined points and things like that. So we're a long way away from theory. But you can see the conflict. I mean, in a sense, it was reflected in what Yvette was saying, because you see in quantum mechanics, you do have times, and it's slicing the space-time up with these parallel three surfaces, if you like. In general relativity, you don't have that. Special relativity, you don't have that. So in order to reconcile these ideas, you've got to modify both theories. And I think that's certainly true. But
something interesting about the equations is that in quantum mechanics, you have the Schrödinger equation. And as I was saying, you treat space and time differently, not only at the level that one is an operator and the other one is a parameter, but also in terms of the derivative, one being a second derivative, one being a first derivative. But something also very interesting is that in the Schrödinger equation, you have a slot for the potential. So you give me a potential and I put it there and I can solve the Schrödinger equation. And if you go to, I don't know, equations like the Klein-Gordon equation, in which it does treat space and time at an equal footing, and you can interchange them, they're both second derivatives and so on, then in that case, you have a slot for the metric. But we do not have an equation that has a slot for both a potential and a metric at the same time, and that treats time, space and time in this sort of equal footing. And I think that, I mean, I don't know if such an equation exists, but it's just interesting to see how they're different in those senses.
So it's ironic that Schrödinger first tried the wave equation, I think, and he had them on an equal footing, was more relativistic. And then he dropped the relativistic. Yeah.
So just to amplify David Brin's question, do you envisage some sort of future understanding where general relativity and quantum mechanics emerge as limiting cases of some sort of central theory, or instead they really are in the future different things which can be made to interface, if you like, in the middle?
I think limiting this first point of view is what I would argue for.
How about the others?
Both of them are limiting versions of the new theory that we don't have. But of course, you can say anything about a new theory that we don't have.
Right. But both of them have been tested. Both of them have been tested with amazing accuracy and precision in their respectively regimes, right? So, and then there is another scale at which you would expect them that they interplay, which is the scales we don't understand, but they would have to have the right limits, because that's what we see in experiments every day.
Well, I guess
Sorry, I'd like to actually respond to that, Roger. It's not the case, what you just said. The CWL theory does encompass both theories. It's moreover shown to be consistent internally. So the only real question now is, does it agree with experiment? But to say that there is no theory which has as limiting cases GR and quantum mechanics is simply not true. And in fact, string theorists would argue the same. They would argue that string theory manages to do both. You may not like these theories, but to say that they don't exist is not correct.
Well, I don't say they don't exist. I just would say they're not the right theory in that case.
Well, that's not what you said. You actually said there is no such theory. So
Okay.
I think one can
Hendrik,
think about that.
do you have anything to add? And Dirk, on this question?
Oh, I think there will be indeed a theory that will combine them in a very elegant way, and we'll see the limits one and the other. And I think even Roger mentioned that he got some breakthrough recently on split octonion theory and so forth.
Oh yes.
It actually happened that I've been working on that for 5 years as a hobby.
Yeah,
and I think, but just crazy ideas where things seem to come together somehow.
Well, it seems to underlie the quantization of twistor space.
Mm-hmm. Yes.
In a surprising way. No, there was a thing I hadn't quite appreciated until 2 days ago.
Right. So
and it really works very nicely. What it tells us, I have no idea. I'm hoping it might resolve some of the questions of CCC, where you seem to lose some symmetry when you cross over from one eon to the next, or really when you have some mass fade out, which is not really. You need some underlying. I wouldn't call it a theory, but some underlying background, which is not quite what we had in mind before. And I think that split octonians, they do fit very well with twistor theory in a way which
it's probably a small extension of it, or it's wider than twistor theory. Is that? But anyway, I think we are getting off topic.
It's quantized twistor theory. You have to put the quantum. That's the key thing. You have to put quantum commutators in. Mm-hmm. And then you do directly get the split octonion. I mean, I didn't know this when I gave the talk, the twistor talk, which I gave last Friday, and I just thought I had the idea. I didn't have it quite right.
Okay.
Well, I was thinking, Dirk, I think, do you have a thought on this sort of meta theory that what it might have?
You mean me, right? So
Hendrik, sorry, Hendrik. Dirk,
yes,
you did mention.
Dirk responded already. So
yes,
I would of course say, hey, come on, I'm the experimentalist. What do you want from me? Yeah. So but I have to say, it would be, I mean, absolutely amazing. Yeah? So to find something new, which is solving some of the problems, some of the issues. Yeah, I'm totally up for it. I have no idea what it is, but I'm totally up for it.
And I think that Sabine Hossenfelder would disagree with Dirk that it's an elegant theory. It might be quite quite horrible and unelegant.
Okay, well.
I don't know. I agree more with you, Dirk, that it might be beautiful and elegant, but there's other points of view.
Sure. Okay, well let's hope for elegance and beauty, and let's and it's clear that the whole audience has got, Roger has set them a homework problem to be solved overnight, and I want to thank especially the 4 speakers as well as Roger for their excellent and for me very instructive and stimulating contributions, and for participating in the spirit of this meeting, in this discussion afterwards. And I'm told by the organizers that you'll be paid overtime rates for the time after 12:30. So thank you very much indeed. Look forward to seeing everybody for another exciting session tomorrow, I think at the same time. Do any of you, this one's on consciousness. Do any of the organizers want to add anything before we close down the screen?
Yes. Thank you, Roger Blandford, for doing an excellent job chairing. Thanks, Yvette, Hendrik, Dirk, and Philip for wonderful, interesting talks that spread across disciplines. I was able to follow a lot of it, and I'm sure most people were. We'll have to have another conference on split octonions and twistor theories for Roger's next birthday or some other occasion. And I do want to mention that in addition to this being Roger's birthday week, today is Abby's birthday. Those of you who've been to our conferences know Abby. So we'll join her in with the celebration on Friday for Roger. And thanks again to both Rogers for this and the speakers. And I think it was a great day. And we'll close out with the video. Thank you all very much. We'll see you tomorrow for Consciousness.
The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with 1/2 to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity.